उसको इस वीडियो में नहीं करेंगे। इस वीडियो में क्या, अल्डेहाइड, कीटोन, कार्बोक्सिलिक एसिड और अमाइंस और बायोमॉलिक्यूल्स, इस तीनों चैप्टर्स को वन शॉट में रीड करने वाले एनसीईआरटी रीडिंग। सो स्टार्ट करते हैं भाई इसको। और भाई थोड़ा गले में खराश हो गया था क्योंकि लगातार ये रीडिंग हो रहा था, तो उससे तो प्रॉब्लम के लिए सॉरी ब्रो। सो एल्डेहाइड, कीटोन एंड कार्बोक्सिलिक एसिड, carbonyl compounds are utmost importance to organic chemistry. They are constituents of fabrics, flooring, plastics, and drugs. In the previous unit, you have studied organic compounds with functional group containing carbon-oxygen single bonds. In this unit, we will study about organic compounds containing carbon-oxygen double bonds, CO called carbonyl group, which is one of the most important functional group in organic chemistry. In aldehyde, the carbonyl group is bonded to a carbon and hydrogen, while in the ketones it is bonded to two carbon atoms. The carbonyl compound in which carbon of carbonyl group is bonded to carbon or hydrogen and oxygen of hydroxyl moiety OH are known as carboxylic acid, while in compound where carbon is attached to carbon or hydrogen and nitrogen of NH2 moiety or two halogen are called amides and acyl halides respectively. Ester and anhydrides are derivative of carboxylic acid. The general formula of these classes of compounds are given below. Aldehyde RCHO, ketone, this is carboxylic acid, and this is acyl halides or halogen, and this is amide RCONH2, and this is ester, this is acid anhydride. Aldehyde ketones carboxylic acid are widespread in plant and animal kingdoms. They play an important role in biochemical processes of life. They add fragrance and flavor to nature. For example, vanillin from vanilla beans, salicylaldehyde from meadow sweets, and cinnamaldehyde from cinnamon have very pleasant fragrance. This is vanillin. So we can see aldehyde OH group and OCH3 group, and this is salicylaldehyde. It contains aldehyde group and alcohol. Cinnamaldehyde, this contains allylic aldehyde as a functional as a substituent. No, this is functional groups aldehyde, and this is allylic aldehyde attached to this benzene. They are used in many food product and pharmaceutical to add flavors. Some of these family are manufactured to use as solvent, that is acetone, and for preparing materials like adhesive paints, resins, perfumes, plastics, fabrics, etc. 12.1 Nomenclature and structure of carbonyl groups. 12.1.1 Nomenclature. First, aldehydes and ketones. Aldehyde and ketones are simplest and most important carbonyl compounds. There are two systems of nomenclature of aldehydes and ketone. A common name. Aldehydes and ketone are often called by their common name instead of IUPAC name. The common name of most aldehydes are derived from common name of corresponding carboxylic acids by replacing the ending IC of acid with aldehyde. At the same time, the names reflects Latin Greek terms for the origin source of acid or aldehyde. The location of substituent in the carbon chain is indicated by Greek letter alpha, beta, gamma, delta, etc. The alpha carbon being the one directly linked to aldehyde group, beta carbon the next, and so on. For example, this is acetaldehyde, this is benzaldehyde, and this is beta bromobutyraldehyde. So this is alpha carbon and this is beta. So this is common name. The common name of ketone are derived by naming the alkyl or aryl groups bonded to carbonyl group. The location of substituent are indicated by Greek letter alpha, alpha dash, beta, beta dash, and so on. Beginning with the carbon atom next to the carbonyl group, indicated is alpha, alpha dash. Some ketone have historical common names. The simplest dimethyl ketone is called acetone. Alkyl phenyl ketones are usually named by adding the name of acyl group as prefix to the word phenone. For example, this is acetone, this is acetophenone, this is propiophenone, this is benzophenone. B. IUPAC name. The IUPAC name of open chain aliphatic aldehyde and ketones are derived from names of corresponding alkanes by replacing the ending "e" with "al" and "one" respectively. In case of aldehyde, longest carbon chain is numbered starting from the carbon of aldehyde group, while in case of ketone, the numbering begins from the end nearer to carbonyl group. The substituents are prefixed in alphabetical order along with numerals indicating their position in carbon chain. The same applies to cyclic ketone, where carbonyl carbon is numbered 1. When the aldehyde group is attached to a ring, the suffix carbaldehyde is added after full name of cycloalkane. The numbering of the ring carbon atom starts from carbon atom attached to the aldehyde group. The name of simplest aromatic aldehyde carrying aldehyde group on a benzene ring is benzene carbaldehyde. However, the common name of benzaldehyde is also accepted by IUPAC name. Other aromatic aldehyde are hence named as substituent benzaldehyde. This is ethanol, 1 2 carbon. This is 1 2 3 4 5 6 7. So 4 bromo, 3 methyl heptanol, and this is 1 2 3. So 3 methyl cyclopentanone, and this is cyclohexanol carbaldehyde. This is 1 2 3 4 5 pen 2 enol, and this is 1 2 3. So 1 phenyl propane 1 on, and this is 3 oxopentanol. So 1 2 3 4 5 3 oxopentanol, and this is 1 2 3 4 5 2, 4 dimethyl pentane 3 and this is 1 2 3 4 nitrobenzene carbaldehyde, and 1 2. If there are more than same functional group attached to more than one carbon, then we exclude this group from this chain. So 1 2 3 means propane 1 2 3 tricarbaldehyde. Note: to give identical treatment to all aldehyde group, the compound is named as shown below. The common name of and IUPAC name of aldehyde and ketone given in table 12.1. So this is formaldehyde, IUPAC name is methanol. This is acetaldehyde, IUPAC name is ethanol. This is isobutaldehyde, IUPAC name is 2-methylpropanol, and so on. And this is phthaldehyde, and IUPAC name is benzene 1,2 dicarbaldehyde, and so on. This is methyl oxide, and IUPAC name is 4-methyl pent 3-enol. 12.1.2 Structure of carbonyl group. The carbonyl carbon atom is sp2 hybridized and form 3 sigma bonds. The fourth valence electron of carbon remain in p orbital and form pi bond with oxygen by overlap with p orbital of an oxygen. In addition, the oxygen atom also has 2 non-bonding electrons pair. Thus, the carbonyl carbon and the 3 atoms attached to it lie in the same plane, and pi electrons cloud in above and below this plane. The bond angle are approximately 120 as expected of trigonal coplanar structure. Orbital diagram for the formation of carbonyl group. So This carbon and oxygen form sigma bond, and this is sp2 hybridized, and also pi bond formed between carbon and oxygen. The carbon oxygen double bond is polarized due to higher electronegativity of oxygen relative to carbon. Hence the carbon is an electrophilic Lewis acid, and carbonyl oxygen a nucleophilic Lewis base center. Carbonyl compounds have substantial dipole moment and are polar than ethers. The high polarity of carbonyl group is explained on the basis of resonance involving neutral A and dipolar B structure as shown. So here is resonating structure in carbonyl group. 12.2 Preparation of aldehyde and ketones. Some important methods for preparation of aldehyde and ketone are as follows. 12.2.1 Preparation of aldehyde and ketones. First, by oxidation of alcohol. Aldehyde and ketone are generally prepared by oxidation of primary and secondary 1 degree and 2 degree alcohols respectively, as we have studied in hydrocarbon chapter 11th in class 12th. Second, by dehydrogenation of alcohol. This method is suitable for volatile alcohol and is for industrial applications. In this method, alcohol vapors is passed over heavy metals like silver and copper. Primary and secondary alcohol give aldehyde and ketone respectively. Unit 11, class 12th. Third, from hydrocarbons. First, by ozonolysis of alkenes. As we know, ozonolysis of alkenes followed by reaction with zinc dust and water give aldehyde. Ketone or a mixture of both depending on substituents pattern of alkene. Second, by hydration of alkynes. Addition of water to ethine in the presence of H2SO4 and HgSO4 give acetaldehyde. All other alkynes give ketones in this reaction. Unit 13, class 11th. 12.2.2 Preparation of aldehydes. First, from acyl chloride or acid chloride. Acyl chloride or acid chloride is hydrogenated over catalyst palladium or barium sulfate. This reaction is called Rosamond reduction. So this benzoyl chloride react with H2 in the presence of palladium and BaSO4. This form benzaldehyde, and this is this is Lindlar catalyst. Second, from nitriles or ester. Nitriles are reduced to corresponding amine with stannous chloride in the presence of hydrochloric acid, which on hydrolysis give corresponding aldehyde. So this is RCN. Nitrile react with SnCl2 and HCl form RCH11NH. In presence of water, it form aldehyde. This reaction is known as Stephan reaction. Alternatively, nitriles are selectively reduced by diisobutyl aluminum hydride diol H to amines followed by hydrolysis of aldehyde. So this nitrile in the presence of diol H and water form aldehyde, and this this nitrile also in presence of diol H form aldehyde. Similarly, ester are also reduced to aldehyde with diol H. So this ester also reduced to aldehyde in presence of diol H and water. Third, from hydrocarbon. Aromatic aldehyde, benzaldehyde and its derivative are prepared from aromatic hydrocarbon by following method. First, by oxidation of methyl benzene. Strong oxidizing agent oxidize toluene and its derivative to benzoic acid. However, it is possible to stop oxidation at aldehyde stage with suitable reagent that convert the methyl group to an intermediate that is difficult to oxidize further. The following methods are used for this purpose. A. Use of chromyl chloride CrO2Cl2. Chromyl chloride oxidize methyl group to chromium complex, which on hydrolysis give corresponding benzaldehyde. So this toluene in presence of chromium chloride and CS2 form chromium complex, and this in presence of water form benzaldehyde, and this reaction is known as Itard reaction. B. Use of chromic oxide CrO3. Toluene or substituted toluene is converted to benzaldehyde diacetate on treating with chromic oxide in acetic anhydride. The benzaldehyde diacetate can be hydrolyzed to corresponding benzaldehyde with aqueous acid. So this is toluene in presence of uh, chromic oxide and this and, and acetic anhydride. It at 273 to 283 Kelvin it form this intermediate. No, this is not intermediate. uh, this is benzaldehyde diacetate, and in presence of water it form benzaldehyde. Water and heat. Second, by side chain chlorination followed by hydrolysis. Side chain chlorination of toluene give benzyl chloride, which on hydrolysis give benzaldehyde. This is commercial method of manufacture of benzaldehyde. So toluene in presence of chlorine and HNO or sunlight form benzyl chloride, and it in presence of water and 100 degrees Celsius form benzaldehyde. Third, by Gutterman-Koch reaction. When benzene or its derivative is treated with carbon monoxide or hydrogen chloride in presence of anhydrous aluminum chloride or cuprous chloride, it gives benzaldehyde or substituted benzaldehyde. So benzene in presence of carbon monoxide HCl and anhydrous AlCl3 and copper chloride form benzaldehyde. This reaction is known as Gutterman-Koch reaction. 12.2.3 Preparation of ketones. First, from acyl chlorides. Treatment of acyl chloride with dialkyl cadmium prepared by the reaction of cadmium chloride with Grignard reagent gives ketone. So this Grignard reagent plus cadmium chloride form R2CD plus MgHCl, and this acyl chloride in presence of R2CD form these ketones plus cadmium chloride. Second, from nitriles. Treating a nitrile with Grignard reagent followed by a hydrolysis yield ketone. So this in nitrile react with this Grignard reagent. It in the presence of ether form this intermediate, and after reaction with water this form propiophenone. This is a common name, and IUPAC name is 1-phenyl propane. So 1 2 no sorry 1 2 3. So 1-phenyl propane is IUPAC name. Third, from benzene or substituted benzene. When benzene or substituted benzene is treated with acid chloride in the presence of anhydrous aluminum chloride, it affords the corresponding ketone. This reaction is known as Friedel-Crafts acylation reaction. So benzene with aryl or acyl chloride in presence of anhydrous AlCl3, this form and this type of ketone. Physical property 12.3. The physical property of aldehyde and ketone are described as follows. Methanol is a gas at room temperature. Ethanol is a volatile liquid. Other aldehyde and ketone are liquid or solid at room temperature. The boiling point of aldehyde and ketone are higher than the hydrocarbons and ether of comparable molecular mass. It is due to weak molecular association in aldehyde and ketone arising out of the dipole-dipole interaction. Also, their boiling point are lower than those of alcohol of similar molecular masses due to absence of intermolecular hydrogen bonding. The following corresponding molecular masses 58 to 60 are ranked in order of increasing boiling points. So N-butane, and this is methoxyethane, this is propanol, acetophenone, and this is propane 1-ol. So on increasing molecular masses, boiling point increases. On increasing branching, boiling point is decreases. So propane 1 mole contain 1 2 3 carbon, and this is OH. And but these contain hydrogen bonding, so its boiling point is more than comparable masses of other organic compounds. The lower members of aldehyde and ketones such as methanol, ethanol, and propanol are miscible with water in all proportion because they form hydrogen bonding with water. So this is ketone in presence in with water form hydrogen bonding. So this is miscible in water. However, solubility of aldehydes and ketone decreases rapidly on increasing the length of alkyl chain. All aldehyde and ketone are fairly soluble in organic solvent like benzene, ether, methanol, chloroform, etc. The lower aldehyde have sharp pungent odor. As the size of molecule increases, the odor becomes less pungent and more fragrant. In fact, many natural occurring aldehyde and ketones are used in the blending or perfume and flavoring agents. 12.4 Chemical reactions. Since aldehyde and ketone both possess carbonyl functional group, they undergo similar chemical reactions. First, nucleophilic addition reactions. Contrary to electrophilic addition reaction observed in alkenes, refer in Unit 13 Class 11, the aldehydes and ketone undergo nucleophilic addition reaction. First, mechanism of nucleophilic addition reaction. On nucleophilic attack, the electrophilic carbon atom of polar carbonyl group from a direction approximately perpendicular to the plane of sp2 hybridized orbital of carbonyl carbon. The hybridization of carbon changes from sp2 to sp3 in this process, and a tetrahedral alkoxide intermediate is produced. This intermediate captures a proton from the reaction medium to give the electrically neutral product. The net result is addition of nucleophile 2 and H plus across the carbon oxygen double bond as shown in figure 12.2. So here is nucleophilic attack of carbonyl carbon. So this is planar molecule after and nucleophile react with this carbon. First step is slow and this is planar, and intermediate is tetrahedral, and second step is fast in presence of H plus or acid. This is addition product. Addition product is also tetrahedral. Second, reactivity. Aldehyde are generally more reactive than ketone in nucleophilic addition reaction due to steric and electronic region. So aldehyde generally more electronegative than ketone due to two reasons: electric and steric and electronic regions. Sterically, the presence of two relative large substituents in ketones hinder the approach of nucleophile to carbonyl carbon than in aldehyde having only one such substituent. Electronically, aldehyde are more reactive than ketones because two alkyl groups reduce the electrophilicity of the carbonyl carbon more effectively than in former. Third, some important example of nucleophilic addition and nucleophilic addition elimination reactions. A. Addition of hydrogen cyanide (HCN). Aldehydes and ketone react with hydrogen cyanide (HCN) to yield cyanohydrins. This reaction occurs very slowly with pure HCN. Therefore, it is catalyzed by base and the generated cyanide ion Cn- being strong nucleophile readily add to carbonyl compound to yield corresponding cyanohydrins. Cyanohydrins are useful synthetic intermediates. So this is cyanohydrin structure. HCN react with OH minus forms Cn minus and H2O, and Cn minus react with carbonyl group. This form tetrahedral intermediate. In presence of acid or S plus, this forms cyanohydrin. B. Addition of sodium hydrogen sulfide. Sodium hydrogen sulfide add to aldehyde and ketone to form addition product. The position of the equilibrium lies largely to the right hand side of most aldehyde and to the left for most ketone due to steric region. The hydrogen sulfide addition compound in water soluble and can be converted back to the original carbonyl compounds by treating it with dilute mineral acid or alkali. Therefore, these are useful for separation and purification of aldehyde. So this is sodium hydrogen sulfide, and in this react with carbonyl group to form this intermediate, and in presence of proton transfer, and after proton transfer this form bisulfide addition compound. This is crystalline. Third, addition of Grignard reagent. This we already studied in class unit 11, class 12th. D. Addition of alcohols. Aldehyde react with one equivalent of monohydric alcohol in the presence of dry hydrogen chloride to yield alkoxy alcohol intermediate known as hemiesters, which further react with one more molecule of alcohol to give alpha a gem dialkoxy compound known as acetal as shown in the reaction. Ketone react with ethylene glycol under similar condition to form cyclic product known as ethylene glycol ketones. Dry hydrogen chloride protonates the oxygen of carbonyl compounds and therefore increase the electrophilicity of carbonyl carbon, facilitating the nucleophilic attack of ethylene glycol. Esters and ketones are hydrolyzed with aqueous mineral acid to yield corresponding aldehyde and ketone respectively. So this aldehyde in presence of ROH and HCl form a hemicestal, and in presence of ROH and H plus they form acetal plus water. This ketone in presence of ethylene glycol, this form HCl, and HCl plus dilute HCl form ethylene glycol ketone. This is cyclic structure plus water. E. Addition of ammonia and its derivative. Nucleophiles such as ammonia and its derivative NH2Z add to the carbonyl group of aldehyde and ketones. The reaction is reversible and catalyzed by acid. The equilibrium favors the product formation due to rapid dehydration of the intermediate to form C double bond NZ. Z is alkyl or aryl, OH NH2, C6H5 aniline, NSCONH2, etc. So this carbonyl group will react to ammonia derivative, form this intermediate, and this form this ammonia derivative plus water. Table 12.2. Some unsubstituted derivative of aldehyde and ketone C double bond En Z. So this is Z, this reagent name, and carbonyl derivative, and this is product. If Z is H and reagent this present in ammonia, this react with carbonyl compound derivative, this form carbonyl derivative C double bond NH2. This is known as imine, and reagent amine with R alkyl group form C double bond NR. This is known as C base, and alcohol from hydroxyl amine form C double bond NOH. This product name is oxime, and if Z is NH2, this obtained from hydrogen, then carbonyl derivative is C double bond NH2, and this is known as hydrazone. And if Z is NH attached to benzene ring, this obtained from phenyl hydrazine, then carbonyl derivative is this compound, this is known as phenyl hydrazone. And if Z is this and reagent, this obtained from 2,4 dinitrophenyl hydrazine, this form 2,4 dinitrophenyl phenyl hydrazone. And if Z is this obtained from semi-carbazide, and we get carbonyl derivative. This is known as semi-carbazone. 2,4 DNP derivative are yellow, orange, red solids useful for characterization of aldehyde and ketones. Second, reduction. First, reduction to alcohol. Aldehydes and ketones are reduced to primary and secondary alcohol respectively. So aldehyde to primary and ketone is secondary alcohol respectively by sodium borohydride, NaBH4, and lithium aldehyde, lithium aluminum hydride, LiAlH4, as well as catalytic hydrogenation. We have already read this in unit 11 in class 12th. Second, reduction to hydrocarbon. The carbonyl group of aldehyde and ketone is reduced to CH2 group on treatment with zinc amalgam and concentrated hydrochloric acid. This is known as Clemenson reduction. Or with hydrazine followed by heating with sodium or potassium hydroxide in high boiling solvents such as ethylene glycol, Wolff-Kishner reaction. So this is Clemenson reduction. In this reaction, this ketone react with ZnHCl. In Clemenson reaction, ZnHG and HCl is reagent and is formed alkene plus water. And if ketone react with NH2 and water, this form this amine derivative, and this react with KOH in ethylene glycol and heat it form this alkane product plus water. This is known as Wolff-Kishner reduction. So in Wolff-Kishner reaction, reagent is NH2 water, and in Clemenson reaction, reagent is ZnHCl plus water. Berhard Tolen was a professor chemistry at University of Göttingen, Germany. 3. Oxidation. Aldehyde differ from ketone in their oxidation reaction. Aldehyde are easily oxidized to carboxylic acid on treatment with common oxidizing agent like nitric acid, potassium permanganate, potassium dichromate, etc. Even mild oxidizing agent, mainly toluene reagent and Fehling reagent, also oxidize aldehyde. So this is aldehyde. In presence of toluene reagent and Fehling reagent, this is oxidized to carboxylic acids. Ketones are generally oxidized under vigorous conditions, that is, strong oxidizing agent and at elevated temperature. Their oxidation involves carbon-carbon bond cleavage to afford a mixture of carboxylic acid having lesser number of carbon atoms than parent ketone. So this ketone react in vigorous conditions. This form this carboxylic acid, and from this two type of carboxylic acid by cleavage of C1C2 bond. So this type of compounds form. This is formed by breaking up this bond, and this compound is formed by breaking up 2 and 3 carbon. The mild oxidizing agent given below are used to distinguish aldehyde and ketone. So we can distinguish aldehyde and ketone by following reagents. First, Tollens test. On warming an aldehyde with freshly prepared ammonical silver nitrate solution or toluene reagent, a bright silver mirror is produced due to formation of silver metal. The aldehyde are oxidized to corresponding carboxylate anion. The reaction occur in an alkaline medium. So this aldehyde in presence of ammonical silver nitrate solution form RC11O minus plus silver. This is this gives bright silver mirror test. Second, Fehling test. Fehling reagent comprises of two solutions, Fehling solution A, This contain two solution A and B. So A and failing solution B. Failing solution A is aqueous copper sulfate. So this is aqueous copper sulfate, and failing solution B is alkaline sodium potassium tartrate Rochelle salt, and B is sodium potassium tartrate. This is known as Rochelle salt. These two solutions with failing reagent or reddish brown precipitate is obtained. Aldehyde are oxidized to corresponding carboxylate anion. Aromatic aldehyde do not respond to this test. RCHO plus 2 copper oxide plus in presence of this alkaline group or alkali form RC11O plus red brown PPT. So red brown PPT occur due to presence of Cu2O. In presence of Cu2O, red brown PPT is formed, and this reaction is failing test. Third, oxidation of methyl ketone by haloform reaction. Aldehyde and ketone having at least one methyl group linked to carbonyl carbon atom methyl ketones are oxidized by sodium hypohalite to sodium salt of corresponding carboxylic acid having one carbon atom less than that of carbonyl compounds. The methyl group is converted to haloform. This oxidation does not affect a carbon-carbon double bond if present in molecule. Iodoform reaction with sodium hypoiodide is also used for detection of CH3CO group or CH3CSOH group, which produces CH3CO group on oxidation. So this aldehyde in presence of NaOH form RC11ONA plus CH3 X is equal to these halides. And if this compound 1, 2, 3, 4, this is ketone react with NaOCl, this form 1, 2, 3 some sodium salts compound. This is oxidation of methyl ketone by haloform reaction, and this is iodoform reaction. This is sodium hypoiodide. For reaction due to alpha hydrogen. Acidity of alpha hydrogen of aldehyde and ketone. The aldehyde and ketone undergo a number of reactions due to acidic nature of alpha hydrogen. The acidity of alpha hydrogen atom of carbonyl group is due to strong electron withdrawing effect of the carbonyl group and resonance stabilizing of conjugate base. So this is aldehyde, this is ketone or some aldehyde group. So due to alpha hydrogen, how it react we are going to study. First, aldol condensation. Aldehyde and ketone having at least one alpha hydrogen undergo a reaction in the presence of dilute alkali as catalyst to form beta hydroxyaldehyde aldol or beta hydroxy ketones ketol respectively. This is known as aldol reaction. So this is ethanol in presence of dilute NaOH form 3-hydroxybutanol, and or this is known as aldol because here is aldehyde and alcohol both group are present, and when heated then water is evolved from this, and this form butanol. This is aldol condensation product. Propane. So ketone in presence of BaOH whole twice barium hydroxide form ketol group. So IUPAC name of this group is 1, 2, 3, 4, 5. So 4 hydroxy 4 methyl pentane 2 on. So on heating this form 1 2 3 4 5 4 methyl pent 3 in 2 all. This is aldol condensation product. The name of aldol is derived from the name of the two functional groups, aldehyde and alcohol, present in the products. The aldol and ketone readily lose water to give alpha beta unsaturated carbonyl compounds, which are aldol condensation product, and the reaction is called aldol condensation. Through ketones give ketones, compound containing a keto and alcohol group. The general name aldol condensation still applies to the reaction of ketone due to similarity with aldehydes. Second, cross aldol condensation. When aldol condensation is carried out between two different aldehyde or ketones, it is called cross aldol condensation. If both of them contain alpha hydrogen atom, it gives a mixture of four products. This is illustrated below by aldol reaction of a mixture of ethanol and propanol. So this is aldehyde, and this is 1 2 3 propanol react with in presence of NOH and heat. It form butanol 2 enol and 2 methyl but 1 2 3 4 5 2 methyl butanol, and these are simple or self aldol products. And if these are cross aldol products, so in simple or self aldol product, same reactant react with same reactant to form product like this 1 2 this ethanol react with same compound to form butanol, and this propanol react with propanol molecule form this compound. In cross aldol product, these both reactants react and form 2 methyl butanol and pentanol, two different molecules. Ketones can also be used as one compound in cross aldol reaction. So this benzaldehyde react with ketone in presence of OH and 293 Kelvin form 1 2 3 1 3 diphenyl propane 2 in 1 1, and this is known as benzyl estophenol. This is major product. Other reaction, there is Cannizzaro reaction. Five other reaction. First, Cannizzaro reaction. Aldehyde which do not have an alpha hydrogen atom undergo self oxidation and self reduction disproportionation reaction on heating with concentrated alkali. In this reaction, one molecule of aldehyde is reduced to alcohol while another is oxidized to carboxylic acid salts. So this is formaldehyde, and this is also formaldehyde. In presence of concentrated KOH and on heating, this form methanol and potassium formate. This is benzaldehyde in presence of concentrated NOH form benzyl alcohol and sodium benzoate. So this is what? This is Cannizzaro reaction. Second, electrophilic substitution reaction. Aromatic aldehyde and ketones undergo electrophilic substitution at ring in which carbonyl group acts as deactivating and meta directing group. So this benzaldehyde in presence of nitric acid H2SO4 at 273 to 283 Kelvin form 1 2 3 or ortho meta para meta nitrobenzene or 3 nitro benzaldehyde or meta benzaldehyde. 12.5 use of aldehyde and ketones. In chemical industry, aldehyde and ketone are used as solvent, starting material and reagent for synthesis of other product. Formaldehyde is well known as formalin, 40% solution used to preserve biological specimen and to prepare bakelite of phenol formaldehyde resin. urea, formaldehyde, glues, and other polymeric products. Acetaldehyde is used primarily as starting material in manufacture of acetic acid. Ethyl acetate, vinyl acetate polymers, and drug benzaldehyde is used in perfumery and in dye industries. Acetone and ethyl methyl ketone is common industry solvents. Many aldehydes and ketone, that is butyldehyde, vanillin, acetophenone, camphor, etc., are well known odors and flavors. So we completed aldehyde and ketone. We are going to cover carboxylic acid. Carbon compounds containing a carboxyl functional group C11OH are called carboxylic acids. The carboxyl group consists of carbonyl group attached to carboxyl group, hence it is named as carboxyl. Carboxylic acid may be aliphatic RC11OH or aromatic ARC11OH. So this is some benzylic group. Depending on group, alkyl or aryl attached to carboxylic carbon, large number of carboxylic acid are found in nature. Some higher member of aliphatic carboxylic acid, 12 carbon to 18 carbon, known as fatty acid. So fatty acid contain 12 to 18 carbons. Occur in nature fat ester of glycerols. Carboxylic acid serve as starting material for several others important organic compounds such as anhydride, ester, acid chlorides, amides, etc. 12.6 Nomenclature and structure of carboxylic group. 12.6.1 Nomenclature. Since carboxylic acid are amongst earliest organic compounds to be isolated from nature, a large number of them are known by their common names. The common name end with suffix iic acid and have been derived from Latin Greek names, their natural sources. For example, formic acid C11OH was first obtained from red ants. Latin formica means ant. Acetic acid CH3COH from vinegar. Latin name acetum means vinegar. Butyric acid CH3CH2CH2C11OH from ranicid butter. Latin butyrium means butter. In the IUPAC name, aliphatic carboxylic acid are named by replacing the ending E in the name of corresponding alkane with oic acid. The numbering of carbon chain, the carboxylic carbon is numbered 1. For naming compounds containing more than one carboxylic group, the alkyl chain leaving carboxylic group is numbered and the number of carboxylic group is indicated by adding the multiplicative prefix dicarboxylic acid, tricarboxylic acid, etc. To the name of parent alkyl chain, the position of C11OH group are indicated by the Arabic numeral before the multiplicative prefix. Some of the carboxylic acid along with their common name IUPAC name listed in table 12.3. Table 12.3 Name and structure of some carboxylic acids. Structure, common name, IUPAC name. So this is formic acid, IUPAC name is methanoic acid, and acetic acid, IUPAC name ethanoic acid, and so on. This is oxalic acid and IUPAC name is ethane dioic acid. This is malonic acid and IUPAC name is propene dioic acid, and this is succinic acid. IUPAC name is butane dioic. So Ohm's gap, it is mnemonics to learn number of carbons. In Ohms there are two carbons. In malonic acid there are 3 carbon. We say that these are homologous compounds. This is benzoic acid, this is phenylacetic acid, this is phthalic acid, this is known as benzene 1,2 dicarboxylic acid. 12.6.2 Structure of carboxyl group. In carboxylic acid, the bond to the carboxylic carbon lie in one plane and are separated by 120 degree. The carboxyl carbon is less electrophilic than carbonyl carbon because the possible resonance structure as shown in figure. So here we can see uh, there is resonance present in carboxylic group. So due to resonance, carboxylic carbon is less electrophilic than carbonyl carbon. 12.7 methods of preparation of carboxylic acid. Some important methods of preparation of carboxylic acid are given as follows. First, from primary alcohol and aldehydes. Primary alcohols are readily oxidized to carboxylic acid with common oxidizing agents such as potassium permanganate, KMnO4 in neutral, acidic or alkaline medium, or by potassium dichromate K2Cr2O7 and chromium trioxide CrO3 in acidic media Jones reagent. So this alcohol react with alkaline KMnO4 in presence of water for carboxylic acid, and 1 decon in presence of Jones reagent. This is Jones reagent CrO3 H2SO4 form decanoic acids. Carboxylic acid are also prepared from aldehyde by use of mild oxidizing agent section 12.4. Second, from alkyl benzenes. Aromatic carboxylic acid can be prepared by vigorous oxidation of alkyl benzene with chromic acid or alkaline potassium permanganate. The entire side chain is oxidized to carboxyl group irrespective of length of side chain. Primary and secondary alkyl group are oxidized in this manner, while tertiary group is not affected. Suitably substituted alkenes are also oxidized to carboxylic acid with these oxidizing reagent. Refer unit 13 in class 11th. So this methyl benzene react with KMnO4 in KOH, presence of KOH and heat form this salt, and it react with water form benzoic acid, and this benzyl derivative react with KMnO4 and KOH form this type of potassium salt, and this react with water to form benzoic acid. Third, from nitriles and amides. Nitriles are hydrolyzed to amides and then to acid in presence of H plus and OH minus H catalyst. Mild reaction conditions are used to stop the reaction at amide stage. So these nitriles hydrolyzed it form amides, and in presence of water this form carboxylic acid. Ethanamide in presence of water and heat form ethanoic acid plus amines. Sorry, this is ammonia. Benzamide in presence of water and heat form benzoic acid plus ammonia. 4, from Grignard reagent. Grignard reagent react with carbon dioxide dry ice to form salt of carboxylic acid, which in turn give corresponding carboxylic acid after acidification with mineral acid. So this is Grignard reagent with carbon dioxide in dry ether form this type of intermediate, or and in presence of water this form carboxylic this is what carboxylic acid. As we know, the Grignard reagent and nitriles can be prepared from alkyl halide. Refer in unit 10 class 12th. The above method 3 and 4 are useful for converting alkyl halide into corresponding carboxylic acid having one carbon atom more than the present in alkyl halide ascending the series. 5 from acyl halides and anhydrides. The acid chlorides, when hydrolyzed with water, give carboxylic acid, or more readily hydrolyzed with aqueous base to give carboxylate ion, which on acidification provide corresponding carboxylic acid. Anhydrides, on the other hand, are hydrolyzed to corresponding acid with water. So this is acid chloride react with water form carbox carboxylic acid and Cl minus, and in presence of water it form RC double bond OH minus, and it react with Cl minus in presence of water form RC double bond OH. Benzoic acid anhydride react with water form 2-benzoic acid, and benzoic ethanoic anhydride in presence of water form benzoic acid and ethanoic acid. So यहाँ से क्या बॉन्ड टूटा, यहाँ से इथेनोइक एसिड बनाया एंड यहाँ से बेंजोइक एसिड. 6 from ester. Acidic hydrolysis of ester give directly carboxylic acid, while basic hydrolysis give carboxylates, which on acidification give corresponding carboxylic acid. So this ethyl benzoate in presence of basic after basic hydrolysis, this give benzoic acid plus ethanol. This is ethyl butanoate in presence of NOH form this compound, this salt plus ethanol, and this react with this react with basic on basic hydrolysis this form butanoic acids. 12.8 Physical properties. Aliphatic carboxylic acid up to 9 carbon atom are colorless liquid at room temperature with unpleasant odors. The higher acid are wax-like solid and practically odorless due to their low volatility. Carboxylic acids are higher boiling liquid than aldehydes, ketones, and even alcohol of comparable molecular masses. This is due to more extensive association of carboxylic acid molecule through intermolecular hydrogen bonding. The hydrogen bond are not broken completely even in vapor phase. In fact, most carboxylic acids exist as dimer in vapor phase or in aprotic solvent. So in vapor state or in aprotic solvent, this carboxylic acid form hydrogen bond and form dimers. Simple aliphatic carboxylic acid having up to 4 carbon atoms are miscible in water. Up to 4 carbon atom miscible in water due to formation of hydrogen bond with water. This solubility decreases with increase in number of carbon atoms. So if number of carbon atom increases, then miscibility decreases in water. Higher carboxylic acid are practically insoluble in water due to the increase in hydrophobic interaction of hydrocarbon parts. Benzoic acid, the simplest aromatic carboxylic acid, is nearly insoluble in cold water. Carboxylic acids are also soluble in less polar organic solvents like benzene, ether, alcohol, and chloroform. This is hydrogen bonding present in carboxylic acid and water. This is best up to 4 carbon, and if mass increases of carboxylic acid, then miscibility decreases. 12.9 Chemical reactions. The reaction of carboxylic acid is classified as follows. 12.9.1 Reaction involving cleavage of OH bond. Acidity. Reaction with metal and alkalis. The carboxylic acid with alcohol evolves hydrogen with electropositive metals and forms salt with alkalis similar to phenols. However, unlike phenols, they react with weaker bases such as carbonates and hydrogen carbonate to evolve carbon dioxide. This reaction is used to detect presence of carboxylic group in an organic compounds. RCOOH carboxylic acid in the presence of sodium form sodium carboxylate plus water, and this carboxylic acid in presence of NaOH, some base form RC1OH Na plus sodium carboxylate ion plus water, and in presence of NaSCO3, this form RC1ONA plus H2O plus CO2. So this is milder basic, and this reaction indicate RC1OH what carboxylic acid is acidic in nature. Carboxylic acid dissociate in water to give resonance stabilized carboxylate anion and hydronium ion. So this carboxylic acids with presence of water form hydronium ion plus, and this RC1O minus. For above reaction, so K equilibrium constant is equal to S3O plus and RC1O minus by S. From this equation, equilibrium constant K is equal to concentration of product by concentration of reactant. From this equation we can get this. So K is equal to K equilibrium and H2O. This is equilibrium constant, solubility in presence of water, solubility constant. This is equal to S3O plus and concentration of product by concentration of reactant. K equilibrium is equilibrium constant and K is acid dissociation constant. K is acid dissociation constant. For convenience, the strength of acid is generally indicated by pKa value rather than Ka value. So acidic strength is indicated by pKa value rather than Ka. pKa is equal to minus log K. So like pH is equal to minus log H plus ion. Like this, pK is equal to minus log Ka. The pK of hydrochloric acid minus 7. So pK of hydrochloric acid minus 7, where pK of trifluoroacid is strongest carboxylic acids. Benzoic acid and acetic acid are 0.23, 4.19 and 4.76. So if pK value increases, then acidity decreases. Smaller the pK, the stronger the acid. So pK increases, acidity decreases. The better it is proton donor. So if it is stronger acid, then is a better strong proton donor. Strong acid have pK value less than 1. The acid with pK value is between 1 and 5 are considered to be moderately strong acid. Weak acid have pK value between 5 to 15, and extremely weak acid have pK value greater than 15. So if extremely weak acid, then pK value is greater than 15. Carboxylic acid are weaker than mineral acid, but they are stronger acid than alcohol, and many simple phenol pK is approx 16 for ethanol and 10 for phenol. In fact, carboxylic acid are amongst the most acidic organic compounds you have studied so far. You already know why phenols are more acidic than alcohols. The higher acidity of carboxylic acid as compared to phenol can be understood similarly. The conjugate base of carboxylic acid or carboxylate anion is stabilized by two equivalent resonance structure, in which the negative charge is at more electronegative atom, oxygen atom. The conjugate base of phenol or phenoxide ion has non-equivalent resonance structure, in which the negative charge is at the less electronegative carbon atom. Therefore, resonance in phenoxide ion is not as important as it is in carboxylate ion. Further, the negative charge is delocalized over two electronegative carbon oxygen atoms in carboxylate ion, whereas it is less effectively delocalized over one oxygen atom, less electronegative carbon atom in phenoxide ion. Thus, carboxylate ion is more stabilized than phenoxide ion, so carboxylic acid is more acidic than phenol. Effect of substituent on acidity of carboxylic acid. Substituents may affect the stability of conjugate base and thus also affect the acidity of carboxylic acid. Electron withdrawing group increase the acidity of carboxylic acid by stabilizing the conjugate base through delocalization of some negative charge by inductive or resonance effect. Conversely, electron donating group decreases the acidity by stabilizing conjugate base. So this electron withdrawing group EWG stabilize the carboxylate anion and strengthen the acid. So it is electron withdrawing group. Uh, this pulls this electron towards itself. So this stabilizes carboxylate anion. So acidity increases, and electron donating group donate electron to carboxylate ion. So this decreases stability. The effect of following group is increases in increase HD order is so minus I increases, or electron withdrawing group as increases, HDT also increases. So CF3 most HD and phenol least HD. Thus, in the following acid arranged in order of increasing HD strength based on pK value. So CF3C11OH due to most electron withdrawing group present in this CF3. This is most HD and this is least HD compounds. Direct attachment of groups such as phenyl or vinyl to carboxylic acid increase the acidity corresponding carboxylic acid, contrary to decrease expected due to resonance effect as shown below. So this is vinyl group and this is vinyl group. Due to resonance, acidity increases. This is because the greater electronegativity of sp2 hybridized carbon to which carbon is attached. The presence of electron withdrawing group or phenyl aromatic carboxylic acid increases their acidity. Electron donating group decreases their acidity. So this is OSS3. This is electron donating group. So this decreases acidity, and benzoic acid is more acidic than this due to absence of electron withdrawing group, electron donating group, sorry, and this electron withdrawing group. So pK value decreases and acidity increases due to electron withdrawing group. 12.9.2 reaction involving cleavage of COH bond. First, formation of anhydride. Carboxylic acid on heating with mineral acid such as H2SO4 or with P2O5 give corresponding anhydride. So these are two ethanoic acid compounds or molecules react with H plus in P2O5 and on heating this dimerize to form ethanoic anhydride. This react and form anhydride, ethanoic anhydride, and water release. Esterification. Carboxylic acid are esterified with alcohol and phenol in presence of mineral acids such as concentrated H2SO4 or HCl gas as catalyst. So this carboxylic acid react with alcohol or phenols, react to form ester plus water. Mechanism of esterification of carboxylic acid. The esterification of carboxylic acid with alcohol is a kind of nucleophilic acid substitution. Protonation of the carbonyl group activates the carbonyl group toward nucleophilic addition or the alcohol. Proton transfer in the tetrahedral intermediate convert the hydroxyl group into OH2 plus group, which being a better leaving group is eliminated as neutral water molecule. The protonated ester so finally loses a proton to give the ester. So this carboxylic acid in presence of acid form this compound, and presence of ROH this form tetrahedral intermediate. After proton transport, after some mechanism form this, and SOH react to form protonated ester in presence of H plus form esters finally. Third reaction with PCl5, PCl3 and SOCl2. The hydroxyl group of carboxylic acid behave like that of alcohol and is easily replaced by chlorine atom on treating with PCl5, PCl3 or SOCl2. Thionyl chloride SOCl2 is preferred because the presence of two products are gaseous and escape the reaction mixture, making the purification of product easier. RC11OH, uh, this carboxylic acid react with PCl5 form RCOCl plus POCl3 plus SCl, and in presence of PCl3 form RCOCl plus S3PO3. These are thionyl, and in presence of thionyl chloride form RCOCl, means acyl chlorides. 4. Reaction with ammonia. Carboxylic acid react with ammonia to give ammonium salt, which on further heating at higher temperature give amides. For example, this etheric acid react with NH3 ammonia form ammonium acetate, and after reduction this form estamide. And this is benzoic acid react with ammonia to form ammonium benzoate, and after hydrolysis this form benzaldehyde. Sorry, these are after removal of water, in presence of water form benzamide. And this is phthalic acid react with ammonia form ammonium phthalate, and after removal of two molecule of water this form phthalimide. Okay, so phthalimide, and after removal of ammonia in strong heating this form phthalimide. So 2025 NEET, this reaction going to be asked. 12.9.3 reaction involving C double bond OH group. First, reduction. Carboxylic acid are reduced to primary alcohol by lithium aluminum hydride, or better with diboron. Diboron does not easily reduce functional groups such as ester, nitro, halo, etc. Sodium borohydride does not reduce the carboxyl group. So this is carboxylic acid in presence of first lithium aluminum hydride or ether or B2H6, and second is water. This form alcohol. Second, decarboxylation. Carboxylic acid loses carbon dioxide to form hydrocarbon when their sodium salt are treated with soda lime, NaOH and CaO in ratio 3:1. So this is very important. Ratio of NaOH and CaOH is 3:1. So R on ONA react with NaOH and CaO in ratio of 3:1 to form RH alkane plus Na2CO3. Alkali metal salts of carboxylic acid also undergo decarboxylation on electrolysis of their aqueous solution and form hydrocarbon having twice the number of carbon atom present in alkyl group of acid. The reaction is known as Kolbe electrolysis. So this reaction is what? This is Kolbe electrolysis, and this is also the process of preparation of alkanes. 12.9.4 substitution reaction in the hydrocarbon part. First, halogenation. Carboxylic acid having an alpha hydrogen are halogenated at the alpha position on treatment with chlorine or bromine in the presence of a small amount of red phosphorus to give alpha carboxylic acid. The reaction is known as Hell-Wolfhard-Jelinski reaction. So this is carboxylic acid in presence of X2 and red phosphorus and water form these aldehyde substituted carboxylic acid compounds, and this replaced the alpha hydrogen. This formed by replacing alpha hydrogen. This is alpha halocarboxylic acid. Second, ring substitution. Aromatic carboxylic acid undergo electrophilic substitution reaction in which the carboxylic group acts as an deactivating and meta-directing group. They, however, do not undergo Friedel-Crafts reaction because the carboxylic group is deactivating and catalyst aluminum chloride Lewis acid get bonded to carboxylic acid. So this benzoic acid react with in presence of concentrate HNO3 and H2SO4 for meta-nitrobenzoic acid, and in presence of Br2 FeBr3 form meta-bromo-benzoic acid. 12.10 Uses of carboxylic acid. Methanoic acid is used in rubber, textile, dyeing, leather and electroplating industries. Ethanoic acid is used as solvent and vinegar in food industries. Hexandioic acid is used in manufacture of nylon 66. सो भाई हेक्साडाइओनिक एसिड देखो, लोग बोलेंगे पॉलीमर तो हट गया, लेकिन देखो यहाँ से क्वेश्चन आ सकता है कि नहीं, लोगों को लगेगा क्या पॉलीमर का क्वेश्चन है, बट दिस इज फ्रॉम carboxylic acid. So hexadioic acid is used for manufacture of nylon 66. Extra of benzoic acid is used in perfumery. Sodium benzoate is used as food preservative. Higher fatty acid is used in manufacture of soaps and detergents. सॉरी ब्रो भाई, इतना इसमें स्टोर कर चुका हूँ मैं, इतना इसमें फाइल हो चुका है कि हैंग मार दे रहा है आईपैड में. Summary. Aldehyde ketones and carboxylic acids are some of important classes of organic compounds containing carboxylic compounds. These are highly polar molecules. Therefore, they boil at higher temperature than the hydrocarbon and weakly polar compounds such as ether of comparable molecular masses. The lower members are more soluble in water because they form hydrogen bond with water. The higher members, because of large size of hydrophobic chain in carbon atoms, are insoluble in water but soluble in common organic solvent. Aldehydes are prepared by dehydrogenation of or controlled oxidation of primary alcohol and controlled or selective reduction of acyl halides. Aromatic aldehyde may also be prepared by oxidation of first methyl benzene with chromyl chloride CrO3 in the presence of acidic anhydride. Second, formylation of arenes with carbon monoxide and hydrochloric acid in presence of anhydrous aluminum chloride. And third is cuprous chloride or by hydrolysis of benzyl chloride. Ketones are prepared by oxidation of secondary alcohols and hydration of alkynes. Ketones also prepared by reaction of acyl chloride with dialkyl cadmium. A good method for preparation of aromatic ketone is Friedel-Crafts acylation of aromatic hydrocarbon with acyl chloride or anhydride. Both aldehyde and ketone can be prepared by ozonolysis of alkenes. Aldehyde and ketone undergo nucleophilic addition reaction into carbonyl group with number of nucleophiles such as SCN, SO4, alcohol or diols. Ammonia derivatives and Grignard reagents. The alpha hydrogen in aldehydes and ketones are acidic. Therefore, aldehyde and ketone having at least one alpha hydrogen undergo aldol condensation in the presence of base with alpha dehydroxy hydroxyaldehyde, aldol, and alpha hydroxyketone, ketol, respectively. Aldehyde having no alpha hydrogen undergo Cannizzaro reaction in the presence of concentrated alkali. Aldehyde and ketone can reduce the alcohol with NaBH4, lithium aluminum hydride, or by catalytic hydrogenation. The carbonyl group of aldehyde and ketone can be reduced by aldehyde group or methynyl group by Clemmensen reduction or Wolff-Kishner reduction. Aldehyde are easily oxidized to carboxylic acid by mild oxidizing reagents such as toluene reagent and Fehling reagents. These oxidation reactions are used to distinguish aldehyde from ketones. Carboxylic acids are prepared by oxidation of primary alcohol and aldehyde and ketone, by hydrolysis of nitriles, and by treatment of Grignard's reagent with carbon dioxide. Aromatic carboxylic acid are also prepared by side chain oxidation of alkyl benzenes. Carboxylic acid are considerably more acidic than alcohol and most simple phenols. Carboxylic acid are reduced to primary alcohol with lithium aluminum hydride or better with diborane in ether solution, and also undergo alpha halogenation with chlorine and bromine in presence of red phosphorus, known as Hell-Olhard-Zelinsky reaction. Methanol, ethanol, propanol, benzaldehyde, formic acid, acetic acid, benzoic acid are highly useful compound in industry. So, aldehyde ketone carboxylic acid, aldehyde ketone कार्बोक्सिलिक एसिड कंप्लीट हो गया भाई. अब करेंगे अपन अमाइंस. तो थोड़ा 5-6 मिनट के लिए रेस्ट कर लो भाई, उससे दिमाग कूल हो जाए. देन वी विल स्टार्ट अमाइंस. सो वी आर गोइंग टू टेक अ ब्रेक फॉर 4 minutes. Then we'll cover amines. मिलते हैं ब्रो शॉर्ट ब्रेक के बाद. मेरी सो भाई, अमाइंस स्टार्ट करने से पहले ब्रेक तो अपना कंप्लीट हुआ। अरे भाई साहब, सो भाई ब्रेक कंप्लीट हुआ, मज़ा किए होगे मस्त एकदम। उम्मीद है आप लोग मज़ा किए होगे। सो भाई, ये चैप्टर स्टार्ट करने से पहले अपन क्या करते हैं, एक अमिताभ बच्चन के जो जी थे, हरिवंश राय बच्चन, मालूम है सबने ये सुना है, फिर भी एक बार मैं सोचता हूँ दोहरा दूँ भाई। जो भी है जुनून लग रहा है कि भाई गिर चुका हूँ, नहीं कुछ होने वाला है उनके लिए। सो कुछ ऐसा है लिखे थे वो, सब कुछ सुना है फिर भी एक बार और। लहरों से डरकर नौका पार नहीं होती, कोशिश करने वालों की हार नहीं होती। नन्ही चींटी जब दाना लेकर चलती है, चढ़ती दीवारों पर 100 बार फिसलती है। मन का विश्वास रगों में साहस भरता है, चढ़कर गिरना गिरकर चढ़ना न अखरता है। आखिर उसकी मेहनत बेकार नहीं होती, कोशिश करने वालों की हार नहीं होती। डुबकियां सिंधु में गोताखोर लगाता है, जा जाकर खाली हाथ लौट कर आता है। मिलते नहीं सहज ही मोती गहरे पानी में, बढ़ता दुगना उत्साह इसी हैरानी में। मुट्ठी उसकी खाली हर बार नहीं होती, कोशिश करने वालों की हार नहीं होती। असफलता एक चुनौती है, असफलता एक चुनौती है, इसे तुम स्वीकार करो। क्या कमी रह गई देखो और सुधार करो। जब तक न सफल हो नींद चैन को त्यागो तुम, जब तक न सफल हो नींद चैन को त्यागो तुम। संघर्ष का मैदान छोड़कर मत भागो तुम। कुछ किए बिना ही जय जयकार नहीं होती, कोशिश करने वालों की कभी हार नहीं होती, कोशिश करने वालों की कभी हार नहीं होती। तो ये हरिवंश राय बच्चन जी का था भाई। कभी भी डिमोटिवेटेड फील करो, इसको दिल में बसा लो भाई, कोशिश करते रहो, हार नहीं होगी। हम में है विश्वास, दिल में है विश्वास, हम होंगे कामयाब एक दिन। सो लेट्स स्टार्ट यूनिट 13 अमाइंस। सो यूनिट 13, देखो ये ओल्ड एनसीईआरटी का, इसीलिए यूनिट 13। नए एनसीईआरटी में यूनिट चेंज हो गया होगा, बिकॉज कई चैप्टर डिलीट भी हुए हैं भाई। सो the chief commercial use of amines is as intermediate in the synthesis of medicines and fibers. Amines constitute an important class of organic compounds derived by replacing one or more hydrogen atom of ammonia molecule by alkyl or aryl groups. In nature, they occur amongst protein, vitamins, alkaloids, and hormones. Synthetic examples include polymers, diesters, and drugs. Two biological active compounds, namely adrenaline, ephedrine, both contain secondary amino group, are used to increase blood pressures. No can a synthetic amino compounds is used as an anesthetic in dentistry. Benadryl, a well-known antihistaminic drug, also contains tertiary amino group. Quaternary ammonium salt are used as surfactants. Diazonium salts are intermediate in the preparation of a variety of aromatic compounds, including dyes. In this unit, you will learn about amines and diazonium salts. First, amines. Amines can be considered as a derivative of ammonia obtained by replacement of one, two, or all the three hydrogen atoms by alkyl or aryl groups. For example, this is methylamine, this is aniline or benzylamine, this is methyl methenamine, and this is diazine dimethyl methenamine. 13.1 Structure of amines. Like ammonia, nitrogen atoms of amines are trivalent and carries an unshared pair of electrons. Nitrogen orbitals in ammonias are therefore sp3 hybridized, and the geometry of amines is pyramidal. Each of three sp3 hybridized orbital of nitrogen overlap with orbitals of hydrogen or carbon depending upon composition of the amines. The fourth orbitals of nitrogen in all amines contains an unshared pair of electrons. Due to presence of unshared pair of electrons, the angle of carbon nitrogen and E E is carbon and or hydrogen is less than 109.5 degree. For instance, it is 108 degree in case of trimethylamine as shown in figure 30.1. So this is unshared pair of electron, and this is CH3 or alkyl group, and this is also alkyl group, and this is also alkyl group, and angle between these two alkyl group is 108 degree. Pyramidal shape of trimethylamine. So this is methyl and 3 methyl group attached to this nitrogen, and this is lone pair. 30.2 classification. Amines are classified as 1 degree, 2 degree and 3 degree depending upon number of hydrogen atom replaced by alkyl or aryl group in ammonia molecule. If one hydrogen atom of ammonia is replaced by R or Ar, we get RNH2 or ArNH2. A primary amine 1 degree. If two hydrogen atom are ammonia or one hydrogen atom RNH2 are replaced by another alkyl group R group, what would you get? You get RNHR dash, secondary amine. The second alkyl or aryl group may be same or different. Replacement of another hydrogen atom in alkyl or aryl group leads to the formation of tertiary amines. Amines is said to be simple when all alkyl or aryl groups are same and mixed when they are different. So NH3, this is 1 degree primary amine, this is secondary amine, this is tertiary amine. 13.3 nomenclature. In common system, an aliphatic amine is named by prefixing alkyl group to amine, that is alkylamine, as one word, and that is methylamine. In secondary and tertiary amine, when two or more group are the same, the prefix di-tri is appended before the name of alkyl group. In IPSC system, primary amines is named as alkylamines. The name is derived by replacement of E of alkane by the word amines. For example, CH3NH2 is named as methanamine. In case more than one amino group is present at different position in parent chain, their position are specified by giving number to the carbon atom bearing NH2 group, and suitable prefix such as di, tri, etc. is attached to the amine. The letter E of suffix of the hydrocarbon is a part retained. For example, NH2 CH2 CH2 NH2 is named as ethane 1,2 diamine. To name secondary and tertiary amines, we use locant N to designate substituent attached to nitrogen atom. For example, this is 1, 2. This is named as N methyl. So N methyl and ethanamine. And CH3 CH2 whole thrice N named as N, diethyl ethanamine. More examples are given in table 13.1. In aryl amines, NH2 group is directly attached to benzene ring. C6H5NH2 is simplest example of aryl amine. In common system, it is known as aniline. It is also an accepted IPSC name. While naming aryl amines according to IPSC system, suffix E of arene is replaced by amines. Thus, IPSC system C6H5NH2 is named as benzenamine. Common IPSC name of some alkyl amines and aryl amines are given in table 13.1. So nomenclature of some alkyl amine and aryl amines. Amines, common names and IPSC name. So this is ethyl amine and IPSC name is ethane amine. And this is N-propyl amine and IPSC name is propane 1 amine and 1, 2. So its IPSC name is N-methyl ethane amine, and it is N, dimethyl methane amine, and so on. And this is aniline, and its IPSC name also aniline or benzenamine. It is important. Aniline, common name, IUPAC name, both we can use aniline for this compound. This is orthotoluidine, also known as 1,2,2-methyl aniline. This is para bromelanin. IUPAC name is 4-bromo-benzene or 4-bromo-aniline. This is AN, so AN CH3 and benzene ring added present here. So this is main branch, so we named that AN dimethyl benzenamine. 30.4 Preparation of amines. Amines are prepared in the following method. First, reduction of nitro compounds. Nitro compounds are reduced to amines by passing hydrogen gas in presence of finely divided nickel, palladium or platinum, and also by reduction with metal in acidic medium. Nitroalkanes can also be similarly reduced to corresponding alkane amines. So these nitro compounds and react to H2PD in presence of ethanol forms aniline, and NO2 in presence of tin HCl or iron HCl form aniline. Reduction with iron scrap and hydrochloric acid is preferred. So this reaction is more preferred because FeCl2 form get hydrolyzed to release hydrochloric acid during the reaction. Thus only a small amount of hydrochloric acid is required to initiate the reaction. Second, ammonolysis of alkyl halides. You have read unit 10 class 12th that the carbon halogen bond in alkyl or benzyl halide can easily cleared by nucleophile. Hence an alkyl or benzyl halide or on reaction with an ethanolic solution of ammonia undergo nucleophilic substitution reaction in which the halogen atom is replaced by an amino NH2 group. This process of cleavage of CX bond by ammonia molecule is known as ammonolysis. The reaction is carried out in sealed tube at 373 Kelvin. The primary amines thus obtained behave as a nucleophile and can further react with alkyl halide to form secondary and tertiary amines and finally quaternary ammonium salts. So this nucleophile reacts to alkyl halide form substituted ammonium salts. So 1 degree alkyl amine react with RX form R2NH 2 degree and then again react with RX form 3 degree alkyl amine and react with RX then form quaternary ammonium salts. The free amine can be obtained from ammonium salt by treatment with strong base. So RNH3X minus the quaternary ammonium salt react with NaOH form RNH2, H2O and NX. Ammonolysis has the disadvantage of yielding mixture of primary, secondary and tertiary amine, also quaternary ammonium salts. However, primary amines is obtained by a major product by taking large scale of ammonia. The order of reactivity of halides is alkyl iodide, then alkyl Br, then RCl. So alkyl iodide is more reactive. Here are some example. तो भाई एक सीरीज लाएंगे जिसमें सारे एग्जांपल्स को एक ही वीडियो में करेंगे, इसलिए एग्जांपल को कवर नहीं कर रहे हैं इसमें. थर्ड, रिडक्शन ऑफ नाइट्राइल्स. Nitriles on reduction with lithium aluminum hydride or catalytic hydrogenation produce primary amines. This reaction is used for ascent of amines series, that is for preparation of amines containing one carbon atom more than the starting amines. So this nitrile react with H2Ni in presence of H2Ni or sodium amalgam, and this is ethanol to form alkyl amines. 4. Reduction of amide. The amides on reduction with lithium aluminum hydride yields amide. So this amide on reduction form amines. Reagent is lithium aluminum hydride and water. 5. Gabriel thalamide synthesis. Gabriel synthesis is used for preparation of primary amines. Thalamide on treatment with ethanolic potassium hydroxide form potassium salt of thalamide, which on heating with alkyl halide followed by alkaline hydrolysis produces the corresponding primary amines. Aromatic primary amines cannot be prepared by this method because aryl halides do not undergo nucleophilic substitution with an anions formed by thalamides. So this is thalamide on react with KOH form this type of salts, and this react with RX form N-alkyl thalamides. And N-alkyl thalamide in presence of aqueous NaOH form phthalic salts and 1 degree amines. This is Gabriel thalamide synthesis. This is very important. 2025 वन क्वेश्चन आने वाला है भाई. 6. Hofmann bromide degradation reaction. Hofmann developed a method for preparation of primary amines by treating an amide with bromine in aqueous or ethanolic solution or sodium hydroxide. In this degradation reaction, migration of an alkyl or aryl group takes place from carbonyl carbon of the amide to nitrogen atom. The amines so formed contain one carbon less than the present in amides. So this is amide reaction with bromine and NaOH form 1 degree amine plus sodium carbonate plus sodium bromide and water. This is Hofmann ब्रोमामाइड डिग्रेडेशन रिएक्शन. सो इस रिएक्शन में शॉर्टकट क्या है भाई, हॉफमैन में इसको उड़ा दो, इसको उड़ा के इन दोनों को ऐड कर दो, अपना प्रोडक्ट मेन प्रोडक्ट आ गया. दिस सिंपल एज दैट. Then 13.5 physical properties. The lower aliphatic amines are gaseous with physic order. Primary amines with 3 or more carbon atoms are liquid and still higher ones are solids. Aniline and other aryl amines are usually colorless but get colored on storage due to atmospheric oxidation. Lower aliphatic amines are soluble in water because they can form hydrogen bonds with water molecules. However, solubility decreases with the increase in molar masses of amines due to increase in size of the hydrophobic alkyl part. Higher amines are essential insoluble in water. Considering the electronegativity of nitrogen of amines and oxygen of alcohol as 3.0 to 3.5 respectively, you can predict the pattern of solubility of amines and alcohols in water. Out of butane 1 all and butane 1 amine, which will be more soluble in water and why? Amines are soluble in organic solvent like alcohol, ether and benzene. You may remember that alcohols are more polar and amines and form stronger intermolecular hydrogen bond than amines. Primary and secondary amines are engaged in intermolecular association due to hydrogen bonding between nitrogen and one and hydrogen on another molecule. This intermolecular association is more in primary amines than in secondary amines, as there are 2 hydrogen atoms available for hydrogen bond formation in it. Tertiary amines do not have intermolecular association due to absence of hydrogen atoms available for hydrogen bonding formation. Therefore, the order of boiling point of isomeric amines are as follows: primary degree, and this boiling point. So primary more boiling point and secondary then tertiary. Intermolecular hydrogen bonding is primary amines is as shown. So this is primary amines, and we can see intermolecular hydrogen bonding means bonding of one molecule to another molecule. Intermolecular hydrogen bonding is primary amines. How it is form primary hydrogen bonding primary amines. Boiling point of amine alcohols and alkanes are almost the same molar mass as shown in figure 13.6. So table 13.2 comparison of boiling points of amines, alcohol and alkanes of similar molecular mass. So these are serial number, these are compounds, these are molar masses, these are boiling points. So for similar molar masses, we can see that here is 1 degree amines, and this is 2 degree amine, this is 3 degree amine. So for equal molar masses, boiling point is maximum for 1 degree amine due to more hydrogen bonding, and least for 3 degree amines due to absence of hydrogen bonding in it. And due to molar mass 74, if molar mass increase, then obviously boiling point also increases. 13.6 chemical reaction. Differences in electronegativity between nitrogen and hydrogen atom and the presence of unshared pair of electron over the nitrogen atom makes amines reactive. The number of hydrogen atom attached to nitrogen atom also decide the course of reaction of amines. That is why primary NH2, secondary and tertiary differ in many reactions. Moreover, amines behave as nucleophile due to presence of unshared pair of electrons. Some of the reactions of amines are described below. So these are some reactions of amines. First, basic character of amines. So amines being basic in nature react with acid to form salts. So this amine reacts with halides. This forms salts. This is acid. And aniline react with HCl form anilinium chlorides. Sorry bhai. Amine salt on treatment with base like NOH regenerate the parent amine. So this is amine salt reacted with base like NOH regenerates a parent amine. So यहाँ पे क्या है, साल्ट है, रिएक्ट कर रहा है क्या बेस से, तो इस साल्ट जिस पेरेंट से बना है वही दोबारा फॉर्म हो जा रहा है. Amine salt are soluble in water but insoluble in organic solvent like ether. This reaction is the basis for separation of amine from the non-basic organic compounds insoluble in water. So this is separation of amines, how we can separate. तो सो ये क्या होगा, amines देखो वाटर में डिजॉल्व हो जा रहा है ना. सो ये देखो हम लोग का जो प्रैक्टिकल ऑर्गेनिक केमिस्ट्री है उसमें भी था एनिलीन का सेपरेशन कैसे करेंगे, तो यहाँ से भी लिंक है भाई वो. द रिएक्शन ऑफ अमाइंस with mineral acid to form ammonium salt shows that these are basic in nature. Amines have an unshared pair of electrons on nitrogen atom due to which they behave as Lewis base. Basic character of amine can be better understood in terms of their Kb and pKb value as explained below. So this amine react with water form R single one NH3 plus OH minus, and equilibrium constant is some product of this molar concentration of products by molar concentrations of reactants multiplication, or KH2. Then we transferred this, and Kb is this is Kb, and pKb is equal to minus log pKb. Larger the value of Kb, smaller the value of pKb, stronger the base. So Kb is larger, pKb is smaller, and basic character is increases. The pKb value of few amines are given in table 13.3. The pKb value of ammonia is 4.75. Aliphatic amines are stronger bases than ammonia due to plus I effect of alkyl group leading to higher electron density on nitrogen atom. Their pKb values lies in range of 3 to 4.22. On other hand, aromatic amines are weaker base than ammonia due to electron withdrawing nature of aryl groups. So if we take this and ammonia is attached to this. So due to electron withdrawing group, the basic character decreases, and if aliphatic group aliphatic allyl attached to this electron donating group, so its basic strength increases as compared to NH3. These are most basic, but these are less basic. So pKb value of methenamine is 3.34. As pKb value increases, basic strength decreases. So list from this table, least basic is ethanamine. Most basic is ethanamine. Due to more plus I electron donating group present in, there are two carbon CH3 CH2 present to give electrons. Then most basic from this table is N-ethyl ethanamine. Due to two electron donating group present in this, then बेसिक स्ट्रेंथ इज एन मिथाइल मिथेनामाइंस. उसके बाद क्या है इथेनामाइंस का. और लिस्ट बेसिक्स जो इस टेबल में सबसे कम बेसिक बेंजीनामाइन ड्यू टू इलेक्ट्रॉन डोनेटिंग नेचर ऑफ बेंजीन ग्रुप, सॉरी इलेक्ट्रॉन विड्रॉइंग ग्रुप ऑफ बेंजीन ग्रुप. दिस बेंजीन रिंग decreases electron density on nitrogen. You may find some discrepancy while trying to interpret the kV value of amines on the basis of plus side minus side effect of substituents present in amines. Beside inductive effect, there are other effects like solvation effect. Beside inductive effect, there are solvation effect, steric effects, etc., which affect the basic strengths of amines. Just ponder over. You may get the answer of the following paragraph. Structure basicity relationship of amines. Basicity of amines is related to their structure. Basic character of amines depend upon ease of formation of cation by accepting a proton from acid. The more stable cation relative to the amines, more basic is the amines. A. Alkyl amine versus ammonia. Let us consider the reaction of alkane amine and ammonia with a proton to compare their basicity. So this is alkane amine react with H plus to form RNH3 N plus, and this reaction is reversible. So this lone pair donated to this H plus and form bond. So this is alkyl group and this is NH3 ammonia. So due to electron releasing nature of alkyl group, if R pushes electron toward nitrogen and does make the unshared electron pair more available for sharing with proton of acid, moreover the substituent ammonium ion formed from amine get stabilized due to dispersal of positive charge by plus I effect of the alkyl group. Hence alkyl amines are stronger base than ammonia. Thus the basic nature of aliphatic amines should increase with increase in the basic alkyl group. This trend is followed in the gaseous phase. The order of basicity of amines in gaseous phase is expected as tertiary amines, secondary amines, then primary amines, then NH3. So basicity of amine in gaseous phase is 3 degree, 2 degree, 1 degree, then pH3. The trend is not regular, but this is not regular in aqueous state as evident in by their pKb values given table 13.3. In the aqueous phase, the substituted ammonium cations get stabilized not only by electron releasing effect of alkyl group but also by solvation, and with water the greater the size of ion, lesser will be solvation. So greater the size of ion, lesser will be solvation, the less stabilized the ion. The order of stability of ions are as follows. So this is decreasing order of extent of hydrogen bonding in water and order of stability of enhance. So stability due to hydrogen bonding, here is 3 hydrogen bonding, and here is 2 and 3 degree, they are 2, so this is more stable. And due to stability due to solvation, greater the stability of substituted amine ammonium cation, stronger should be corresponding amine as base. Thus the order of basicity of aliphatic amine is 1 degree, secondary and then tertiary, which is opposite to inductive effect based order. Secondly, when the alkyl group is small, like CH3 group, there is no steric hindrance to hydrogen bonding. In case of alkyl group is bigger than CH3 group, then there will be steric hindrance to hydrogen bonding. Therefore, the change of nature of alkyl group, that is CH3 to C2H5, result in change in order of basic strength. Thus, there is subtle interplay of inductive effect, solvation effect, and steric hindrance of alkyl group, which decide the basic strength of alkyl amines and aqueous state. The order of basic strength in case of methyl substituted amine and ethyl substituted amine in aqueous solution is given below. So this is ethyl substituted alkyl amine. In this case, 2 degree, then 3 degree, then 1 degree, then NH3. This is in case of alkyl ethyl substituted amine, and this is methyl substituted amine, 1 degree, 2 degree, 1 degree, and 3 degree, then NH3. These are basic strength. B. Aryl amines versus ammonia. pKb value of aniline is quite high. Why is it so? It is because in alanine or other aryl amines, the NH2 group is attached directly to benzene ring. This result the unsaid electron pair of nitrogen atom to be conjugation with benzene ring, and thus making it less available for protonation. If you write different resonating structure of aniline, you will find aniline in resonance hybrid of the following 5 structure. So this is 5 resonating structure present in aniline, but in anilinium ion there is only 2 resonating structures. This is calculate structure resonating structures. So we know that greater the number of resonating structure, greater the stability. Thus you can infer that aniline 5 resonating structure is more stable than anilinium ion. Hence the proton acceptability or the basic nature of aniline or other aromatic amines would be less than that of ammonia. In case of substituted aniline is observed electron releasing group like OCH3, CH3 increases the basic strength, whereas the electron withdrawing group like NO2SO3H, C11OH, X decreases it. So electron withdrawing group decreases basic strength and in aniline, but electron donating group increases basic strength in aniline. Second, alkylation. Amines undergo alkylation on the reaction is alkyl halide. This is present in unit 10 of class 12th. Third, acylation. Aliphatic and aromatic primary amines and secondary amines react with acid chloride, anhydride, and ester by nucleophilic substitution reaction. This reaction is known as acylation. You can consider this reaction as replacement of hydrogen atom NH2 or NH group by acyl group. The product obtained by acylation reaction are known as amide. The reaction is carried out in presence of base stronger than amine, like pyridine, which remove HCl, so formed and shift the equilibrium to right hand side. This ethanamine in presence of base, this form N-ethyl ethanamide plus HCl. This N-ethyl ethanamine in presence of acyl chloride and base, this form N, N diethyl 1,2 ethanamide. This is benzene amine, and this react with ethanoic anhydride 1 2 ethanoic anhydride. It form n phenyl ethanamide 1 2. So this is, sorry, 1 2, or this is also known as external anhydride. Sorry, this is एस्टर, भाई ये क्या बोलेंगे भाई, एस्टानाइलिडी और एस्टानाइलिड, क्या बोलेंगे भाई, एस्टानाइलिड बोलेंगे क्या, एस्टानाइलिड या एस्टनाइड, क्या बोलेंगे यार, प्रोनाउंसिएशन में मेरा प्रॉब्लम हो रहा है ब्रो, आई एम सॉरी, बेसिक सीखना पड़ेगा. एस्टानाइलिड. Amines also react with benzoyl chloride C6H5COCl. This reaction is known as benzylation. Methanamine react with benzoyl chloride. This form N-methyl benzenamide plus hydrochloric acid. What you think is the product of reaction of amine with carboxylic acid? They form salt with amines at room temperatures. 4. Carbyl amine reaction. Aliphatic and aromatic amines on heating with chloroform and ethanolic potassium hydroxide form isocyanide or carbyl amine, which are foul-smelling substances. Secondary and tertiary amines do not show these reactions. This reaction is known as carbyl amine reaction or isocyanide test and is used in test of primary amine. So this is 1 degree amine react with chloroform in presence of KOX and heat form. What is this? This is isocyanide, alkyl isocyanide plus potassium chloride plus water. 5. Reaction with nitrous acid. 3 classes of amine react differently with nitrous acid, which is prepared in situ from mineral acid and sodium nitrite. A primary aliphatic amine react with nitrous acid to form aliphatic diazonium salt, which being unstable liberate nitrogen gas quantitatively and alcohols. Quantitative evolution of nitrogen is used in elimination of amino acid and protein. So this 1 degree amine react with SNO3 in presence of NaNO2 and plus HCl form RN2Cl, and in presence this is diazonium salts. This is known as diazotization reaction. In presence of water form ROH N2 plus HCl. B. Aromatic amines. Aromatic amines react with nitrous acid at low temperature 273 to 78 Kelvin to form diazonium salt, a very important class of compound used for synthesis of variety of aromatic compound discussed in section 13.7. So aniline react with NaNO2 plus HCl at 273 to 275 form benzene diazonium chloride plus NaCl and water. Secondary and tertiary amine react with nitrous acid in a different manner. 6. Reaction with aryl sulfonyl chloride. Benzyl sulfonyl chloride C6H5SO2HCl, which is also known as Hinsberg reagent, react with primary and secondary amine to form sulfonamide. A. The reaction of benzene sulfonyl chloride with primary amine yields an ethyl benzene sulfonyl amide. So this is benzene sulfonyl chloride. This react with 2 degree amine. This form en ethyl benzene sulfonyl amide. This is soluble alkali. So HCN, we can learn this Heisenberg reaction from HCN. This is Heisenberg test 1 degree, 2 degree, 3 degree. If we react this benzoyl sulfonyl chloride or Heisenberg reagent with 1 degree amine, then product is soluble, and if we react with 2 degree amine, then we get insoluble product, and if we react with 3 degree amine, then no reaction take place. The hydrogen attached to nitrogen in sulfonamide is a strongly acid due to presence of a strong electron withdrawing sulfonyl chloride, hence soluble in alkali. So this is 2 degree amine react with Heisenberg reagent, this form soluble compound B in the reaction with secondary amines N, N diethyl benzene sulfonamide is formed. So this Heisenberg reagent react with 2-degree amine to form N, N diethyl benzene sulfonamide. This is insoluble product. Since N and dimethyl benzene sulfonamide does not contain any hydrogen atom attached to nitrogen atom, it is not acidic and hence insoluble in alkali. Third, tertiary amines do not react with benzene sulfonyl chloride. This property of amine reacting with benzene sulfonyl chloride in different manner is used for distinction of primary, secondary and tertiary amine, and also for separation of a mixture of amines. However, these days benzene sulfonyl chloride replaced by para sulfonyl chlorides. Electrophilic substitution. You have read earlier that aniline is in resonance hybrid of 5 structure. Where do you find the maximum electron density in this structure? Ortho and para position to NH2 group becomes center of high electron density. Thus, NH2 group in ortho and para directing and powerful activating group. So, bromination. Aniline react with bromine water and at room temperature to give white precipitate 2,4,6 tribromoaniline. So aniline react with bromine water form 2,4,6 tribromoaniline, and this is white precipitate. The main problem encountered during electrophilic substitution reaction of aromatic amine is that there is very high reactivity. Substitution tend to occur at ortho and para position. If we have to prepare monosubstituted aniline derivative, how can the activating effect of NH2 group be controlled? This can be done by protecting the NH2 group by acetylation with acetic anhydride, then carrying out the desired substitution followed by hydrolysis of substituted amide to substituted amines. This amine react with pyridine and this is acid anhydride to form एस्टेनलीड एस्टेनाइलीड. भाई मेरे को यहाँ प्रॉब्लम आता है यार पढ़ने में. एस्टेनाइलीड and it react with bromine and ethanoic acid form this major product, and this react with water form 4-bromoaniline. The lone pair of electron of nitrogen of acetyl interact with oxygen atom due to resonance as shown in figure. So lone pair of this reaction is as follows. Hence the lone pair of electron on nitrogen is less available. So due to resonance, lone pair of this electron is less available for donation of benzene ring by resonance. Therefore activating effect NHCOCH3 group is less than that of amino group. B nitration. Direct nitration of aniline yield terry oxidation product in addition to nitro derivative. Moreover, in the strongly acidic medium, aniline is protonated to form the anilinium ion, which is meta-directing. That is why beside the ortho and para derivative, significant amount of meta-derivative is also formed. So aniline in with HNO3 and H2SO4 at 8 Kelvin form 51%. This is major product and these are minor products. However, protecting NH2 group by acetylation group with acetic anhydride, the nitration reaction can be controlled by para-nitro derivative can be obtained as major product. Aniline react with acetic anhydride in presence of pyridine form acetaldehyde, and this in presence of nitric acid H2SO4 form para-nitroacetaldehyde plus para-nitroaniline. Sorry, this para-nitroacetaldehyde और एस्टन. भाई इसको क्या पढ़ेंगे, कैसे प्रोनाउंस करें. एक कंप्लीट करने के बाद पक्का मैं जाऊंगा, इसको प्रोनाउंस करूंगा और कभी नहीं भूलने वाला हूँ कैसे। नाइट्रो एस्टिन लीड। अच्छा है। और ये वाटर एल्कोहल से रिएक्शन किया बेस से और एसिड से, देन फॉर्म पैरानाइट्रो एनिलीन। सल्फोनेशन। Aniline react with concentrated sulfuric acid to form anilinium hydrogen sulfate, which on heating with sulfuric acid at 453 to 473 Kelvin produce para-amino benzene sulfonic acid, commonly known as sulfanilic acid, as major product. So aniline in presence of H2SO4 form anilinium hydrogen sulfate, and it react with 453 to 473 Kelvin forms sulfanilic acid, and it form deuterium, and this is reversible, and this is deuterium. So aniline react with H2SO4 to form anilinium hydrogen sulfate, and at 4 on heating it forms sulfanilic acid, and this is form deuterium. Aniline does not undergo Friedel-Crafts reaction, alkylation and acetylation. Due to salt formation aluminum chloride, the Lewis acid, which is used as catalyst. Due to this, nitrogen of aniline acquires positive charge and hence as a strong deactivating group for further reactions. Second, diazonium salts. The diazonium salts have general formula Rn2 plus X minus, where R stand for aryl group, X minus ion may be Cl minus, Br minus, HSO4 minus, Bf4 minus, etc. They are named by suffixing diazonium to the name of parent hydrocarbon from which they are formed, followed by the name anions such as chloride, hydrogen sulfate, etc. The N2 plus group is called diazonium chlorides. For example, this diazonium salt is named as benzene diazonium chloride, and this is benzene diazonium hydrogen sulfate. Primary aliphatic amines form highly unstable alkyl diazonium salt, reference section 30.6. Primary aromatic amines form arene diazonium salts, which are stable for short time in solution at low temperature, 273 to 278 Kelvin. The stability of arene diazonium ion is explained on the basis of resonance. So this is arene diazonium salt, and here we can see resonance. Due to resonance, stability increases in these compounds. This is arene diazonium salt, and how resonance take place depicted in this 4 pictorial diagram. 30% method of preparation of diazonium salts. Benzene diazonium chloride is prepared by a reaction of aniline with nitrous acid at 273 to 278 Kelvin. Nitrous acid is produced in the reaction mixture by reaction of sodium nitrite with hydrochloric acid. The conversion of primary aromatic amines with diazonium salt is known as diazotization. Due to instability of diazonium salt is not generally stored and is used immediately after the preparation. So this is aniline in presence of sodium nitrate NO3 nitrite plus HCl for at 273 to 278 degrees Celsius or 0 degrees Celsius to 5 degrees Celsius form diazonium salt plus NaCl plus water. 13.8 Physical properties. Benzene diazonium chloride is a colorless crystalline solid. It is readily soluble in water and is stable in cold but react with water when warmed. It decomposes easily in dry state. Benzene diazonium fluoroborate is water insoluble and stable at room temperature. 30.9 Chemical reaction. The reaction of diazonium salt can be broadly divided into two categories, namely A. Reaction involving displacement of nitrogen. B. Reaction involving retention of diazo group. A. Reaction involving displacement of nitrogen. Diazonium group, being very good leaving group, is substituted by other groups such as Cl minus, Br minus, I minus, Cn minus and OH minus, which displace nitrogen from aromatic ring. The nitrogen formed escapes from the reaction mixture as a gas. First replacement by halides or cyanide ion. These chloride ion, bromide ion, cyanide ion nucleophiles can easily be introduced in benzene ring in the presence of copper first ions. This reaction is called Sandmeyer reaction. So in Sandmeyer reaction, diazonium salt react with copper first chloride and hydrochloric acid for aryl chloride plus nitrogen gas, and with same with HBr and same with KCN. Alternatively, chlorine or bromine can also be introduced in the benzene ring by treating with diazonium salt solution with corresponding halogen acid in the presence of copper powder. This is referred as Gutterman reaction. So this is benzene diazonium salt, and in presence of copper and HCl form aryl chloride plus nitrogen plus CuX, and in presence of copper and HBr form aryl bromide nitrogen plus CuX. The yield in Sandmeyer reaction is found to be better than Gutterman reaction. So yield in Sandmeyer reaction is found better than Gutterman reaction. Second, replacement by iodide ion. Iodine is not easily introduced into the benzene ring directly, but when diazonium salt solution is treated with potassium iodide, iodobenzene is formed. So this is diazonium salt react with potassium iodide, form aryl iodide plus KCl plus N2. Third, replacement by fluoride ion. When arene diazonium chloride is treated with fluoroboric acid, arene diazonium fluoroborate is precipitated, which on heating decomposes to yield aryl fluoride. So this diazonium salt react with fluoroboric acid, form diazonium fluoroborate, and after heating is formed aryl fluoride plus BF3 plus nitrogen gas. For replacement by hydrogen, certain mild reducing agent like hypophosphorus acid, phosphenic acid, or ethanol reduce diazonium salt to arenes and themselves get oxidized to phosphorus acid and ethanol respectively. This diazonium salt react with S3PO2 plus H2O form aryl hydride plus N2 or benzene. This is benzene. And this is S3PO4. So this oxidize diazonium salt react with ethanol to form this halide, aryl halide plus nitrogen plus ethanol plus hydrochloric acid. 5. Replacement by hydroxyl group. If the temperature of the diazonium salt of a solution allowed to rise up to 283 Kelvin, the salt get hydrolyzed to phenol. So this is diazonium salt reacts to water form phenol plus nitrogen gas plus HCl. 6. Replacement of NO2 group. When diazonium fluoroborate is heated with aqueous sodium nitrite solution in presence of copper, the diazonium group is replaced by NO2 group. So this is diazonium salt reacts with fluoroboric acid, form what is this, इसको क्या बोलेंगे ब्रो? This is called diazonium fluoroborate. So this is diazonium fluoroborate और NaNO2 और कॉपर के प्रेजेंस में हीट कर रहे हैं तो क्या फॉर्म हो रहा है? नाइट्रोबेंजीन प्लस नाइट्रोजन प्लस NaBF4. B reaction involving retention of diazo group, coupling reaction. The azo product obtained have an extent conjugate system having both aromatic ring joined through N double bond N bond. These compounds are often colored and are used as dyes. Benzene diazonium chlorides react with phenol, in which the phenol molecule at its para position is coupled with diazonium salt to form para-hydroxyazobenzene. This type of reaction is known as coupling reaction. Similarly, the reaction of diazonium salt with aniline yield para-aminobenzene. This is an example of electrophilic substitution reaction. So diazonium salt react with phenol, it forms para-hydroxy benzene, and diazonium salt reacts with aniline form para-aminobenzene. So सबसे ये इम्पोर्टेंट बात क्या है भाई, इस रिएक्शन में मोस्ट इम्पॉर्टेंट बात ये है कि देखो एनिलीन रिएक्ट कर रहा है फिनॉल के साथ इन प्रेजेंस ऑफ एल्को सम बेस है ना, तो फॉर्म कर रहा है पैरा हाइड्रोक्सी एजोबेंजीन, दिस ऑरेंज डाई, एंड if this aniline react with this diazonium salt reacts with aniline in presence of acid, तो यहाँ पे देखो एसिड है, तो क्या फॉर्म कर रहा है पैरा अमीनो एजोबेंजीन, दिस इज येलो डाई. ओके, और ये क्या कपलिंग रिएक्शन हो रहा है, तो OH माइनस में बन रहा है ना. (13.10) Importance of diazonium salt in synthesis of aromatic compounds. From the above reaction, it is clear that diazonium salt are very good intermediate for introduction of fluorine, chlorine, bromine, iodine, cyanide, OH, NO2 group into the aromatic ring. Aryl fluoride iodide cannot be prepared direct halogenation. This cyano group cannot be introduced by nucleophilic substitution of chlorine in chlorobenzene, but cyclobenzene can be easily obtained from diazonium salt. Thus, the replacement of diazo group by other group is helpful in preparing those substitutes aromatic compound which cannot be prepared by डायरेक्ट सब्सटीट्यूशन इन बेंजीन और सब्सटीट्यूटेड बेंजीन. कुछ एग्जांपल है, इसको अलग सीरीज लाएंगे, उसमें एग्जांपल रिसीव करेंगे. समरी, amines can be considered as derivative of ammonia obtained by replacement of hydrogen atom with alkyl or aryl group. Replacement of one hydrogen atom of ammonia give rise to structure of the type RNH2 known as primary amine, secondary amine, and characterized by structure R2NH मतलब 2 degree, and tertiary amine 3 degree, denoted by this. Secondary tertiary amines are known as simple amines if alkyl or aryl groups are same, and mixed amine if the group are different. Like ammonia, all the 3 type of amines are one shared electron pair on nitrogen due to which it behaves as Lewis base. Amines are usually formed from nitro compounds, halides, amides, etc. They exhibit hydrogen bonding which influence their physical property. In alkyl amines, a combination of electron releasing steric and hydrogen bonding factors influence the stability of substituted ammonium cations in protic polar solvent and thus affect the basic nature of amines. Alkyl amines are found to be stronger base than ammonia. In aromatic amines, electron releasing and withdrawing groups respectively increases and decreases their basic character. Aniline is weaker base than ammonia. Reaction of amine is governed by availability of unshared pair of electron on nitrogen. Influence of number of hydrogen atom at nitrogen atom on type of reaction and nature of product is responsible for identification and distinction between primary, secondary, and tertiary amine. Para-toluene sulfonyl chloride is used for identification of primary, secondary, tertiary amines. Presence of amino group in aromatic ring enhance the reactivity of aromatic amines. Reactivity of aromatic amines can be controlled by acylation process, that is by treating with acetyl chloride or acetyl anhydride. Tertiary amines like trimethyl amine are used as insect attractants. Aryl diazonium salt, usually obtained by aryl amines, undergo replacement of diazonium group with variety of nucleophiles to provide advantageous method for production of aryl halides cyanide phenol arenes by reductive removal of the diazo group. Coupling reaction of aryl diazonium salt with phenol or aryl amine give rise to formation of azo di. सो अपना अमाइंस भी कंप्लीट हुआ भाई. तो सो एल्डिहाइड 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 कीटोन कार्बोक्सिलिक एसिड कंप्लीट हुआ. अमाइंस कंप्लीट हुआ. वी आर गोइंग टू कवर बायोमॉलिक्यूल्स. तो इसके लिए ब्रेक लेते हैं भाई. इसके लिए अभी हो रहा है 11:15 से 11:15 AM टू 11:20 AM. ब्रेक लेते हैं. देन वी गोइंग टू कवर दिस चैप्टर. इसका चेहरा कौन से कलर में बनाया भाई आज? पिंकी है पैसों वाले को, इसको पिंकी बनाते हैं. ठीक, मिलते हैं भाई 20 मिनट बाद. सो है भाई, क्या हाल चाल? वेलकम बैक टू माय यूट्यूब चैनल. वेलकम बैक. टाइम हो गया भाई रेस्ट. तो स्टार्ट करने से पहले भाई एक कुछ शेर था, तो ऐसा है। वक्त से लड़का जो नसीब बदल दे, इंसान वही जो तकदीर बदल दे। कल क्या होगा कभी मत सोचो, क्या पता कल वक्त खुद अपनी तस्वीर बदल दे। समझ रहा भाई? लोग सोचते हैं कल क्या होगा, क्या होगा, क्या होगा भाई। बहुत तुम मान लो हीरो बन रहोगे, हाँ ये कर लेंगे वो कर लेंगे। नीट का एग्ज़ाम का पेपर लीक हो गया, क्या कर लिया? कट ऑफ जाता था 615, चला गया 150। पूरा वो कल अपना खुद तस्वीर बदल दिया, तो क्या ही कर पाओगे। इसलिए कि पॉजिटिव अपना वर्क करते रहो, जो होगा देखना, बाकी दुनिया भाड़ में जाए। समझे? लेट्स स्टार्ट यूनिट 14 बायोमोलिक्यूल्स। It is harmonious and synchronous progress of chemical reaction in body which led to life. A living system grows, sustains and reproduces itself. The most amazing thing about a living system is that it is composed of non-living atoms and molecules. The pursuit of knowledge of that does not goes on chemically within a living system falls in the domain of biochemistry. Living systems are made up of various complex biomolecules like carbohydrate, protein, nucleic acid, lipids, etc. Protein and carbohydrates are essential constituents of our food. These biomolecules interact with each other and constitute the molecular logic of life processes. In addition, some of simple molecules like vitamins and mineral salt also play an important role in functions of organisms. Structures and function of some of these biomolecules are discussed in this unit. 14.1 Carbohydrate. Carbohydrates are primarily produced by plant and form very large group of naturally occurring organic compounds. Some common examples of carbohydrates are cane sugar, glucose, starch, etc. Most of them have general formula CxH2O whole Y, and they consider as hydrate. They consider as hydrate for of carbon, from where the name carbohydrate was derived. For example, the molecular formula of glucose C6H12O6 fits into general formula C6H2O whole 6, but all compounds which fit into formula may not be classified as carbohydrate. For example, acetic acid CH3COOH fits into this general formula C2H2O whole twice, but is not a carbohydrate. Similarly, rhamnose C6H12O5 is carbohydrate but does not fit in these definitions. A large number of their reactions have shown that they contain a specific functional group. Chemically, the carbohydrate may be defined as optically active polyhydroxy aldehyde or ketone, or the compound which produce such unit on hydrolysis. Some of the carbohydrates which are sweet in taste are also called sugar. The most common sugar used in our home named as sucrose, whereas the sugar present in milk is known as lactose. Carbohydrates are also called saccharides. Greek saccharon means sugar. 14.1.1 Classification of carbohydrates. Carbohydrates are classified on the basis of their behavior on hydrolysis. They have been broadly divided into following three groups. First, monosaccharides. A carbohydrate that cannot be hydrolyzed further to give simpler unit of polyhydroxyaldehyde or ketone is called a monosaccharides. About 20 monosaccharides are known to occur in nature. Some common examples of glucose are glucose, fructose, ribose, etc. Second, oligosaccharides. Carbohydrates that yield 2 or 10 monosaccharides unit on hydrolysis are called oligosaccharides. They are further classified on as disaccharide, trisaccharide, tetrasaccharides, etc. depending on the number of monosaccharides they provide on hydrolysis. Among these, most common are disaccharides. The two monosaccharides units obtained on hydrolysis of disaccharide may be same or different. For example, one molecule of sucrose on hydrolysis give one molecule of glucose and one molecule of fructose, where maltose give two molecule of only glucose. Third, polysaccharides. Carbohydrates which yield a large number of monosaccharide units on hydrolysis are called polysaccharides. Some common examples are starch, cellulose, glucose, gums, etc. Polysaccharides are not sweet in taste, hence they are also called non-sugars. The carbohydrates may also be classified as either reducing or non-reducing sugar. All those carbohydrates which reduce failing solution toluene reagent are referred to as reducing sugars. All monosaccharides, whether aldose or ketose, are reducing sugars. 14.1.2 Monosaccharides. Monosaccharides are further classified on the basis of number of carbon atoms and the functional group present in them. If monosaccharides contain an aldehyde group, it is known as aldose, and if contain a keto group, it is known as ketose. Number of carbon atom constituting monosaccharide is also introduced in number as evident of example in table 14.1. So different type of monosaccharides, number of carbons, general term aldehyde, and if aldehyde present, then what is called, and if ketone is present, ketonic group. If 3 carbon, then general term triose. If aldol present, then aldotriose, and if ketone present, then ketotriose, and so on. 14.1.2.1 Glucose. So glucose occurs freshly in nature as well as in combined form. It is present in sweet fruit and honey. Ripe grapes also contain glucose in large amount. It is prepared as follows. Preparation of glucose. First, from sucrose cane sugar. If sucrose is boiled with dilute HCl or H2SO4 in alcoholic solution, glucose and fructose are obtained in equal amounts. So this is sucrose unhydrolyzed it is boiled in HCl or H2SO4 alcoholic solution, then break down into hydrolyzed into glucose and fructose. Second, from starch. Commercially, glucose is obtained by hydrolysis of starch by boiling with dilute H2SO4 at 393 Kelvin under pressure. Starch or cellulose boiled in water in acidic medium at 393 Kelvin and 2 to 3 atmospheric pressure, it forms glucose. Structure of glucose. Glucose is an aldohexose and is also known as dextrose. It is the monomer of many larger carbohydrates, namely starch, cellulose. It is probably the most abundant organic compound on earth. It was assigned the structure given below on the basis of the following evidence. First, molecular formula was found to be C6H12O6. Second, on prolonged heating with HI, it formed an hexane, suggesting that all the 6 carbon atoms are linked in straight chain. So this is glucose. Glucose react with HI and heat is form N-hexane. Third, glucose react with hydroxylamine to form an oxime and adds a molecule of hydrogen cyanide to give cyanohydrine. This reaction confirms the presence of carbonyl group. So carbonyl group is confirmed by reaction with hydroxylamine. It forms oxime, and 4 glucose get oxidized to 6 carbon carboxylic acid, gluconic acid on reaction with mild oxidizing agent like bromine water. This indicates that carbonyl group is present in aldehyde group. So if you react with bromine water, it forms carboxylic gluconic acid. It contains aldehyde group, and this glucose react with hydrogen cyanide. It forms CSCNOH, and this compound form cyanohydrine. 5. Acetylation of glucose with acetic anhydride gives glucose pentacetate, which confirm the presence of 5 OH group. Since it exists as a stable compound, 5 OH groups should be attached to different carbon atom. So glucose in presence of acetic anhydride form this compound. This is glucose pentacetate. This confirm presence of 5 OH group. 6. On oxidation with nitric acid, glucose as well as gluconic acid both yield dicarboxylic acid, saccharic acid. This indicates the presence of primary alcoholic group in glucose. So glucose after oxidation forms saccharic acid, and gluconic acid also after oxidation this also forms saccharic acid. The exact spatial arrangement of different OH group was given by Fischer after studying many other properties. Its configuration is correctly represented as first, so gluconic acid is represented as second and saccharic acid third. So this is glucose and this is what gluconic acid, and this is saccharic acid. So this is structure of glucose, spatial arrangement. So here aldehyde group 1 2 3 4 5 6 carbon present, and at second carbon OH present at right side, and at third carbon OH present at left side, and fourth and fifth carbon OH present at right side. And this is gluconic acid, and this is what saccharic acid. Glucose is correctly named as dextra rotatory glucose. D before name of glucose represent configuration, whereas plus represent dextrorotatory nature of glucose. Oh sorry, this is D form, and plus so dextrorotatory means it rotates plane light in right direction. It should be remembered that the D and L have no relation with optical activity of the compound. They are also not restricted to letter D and L. See unit 10. The meaning of D and L rotation is follows. The letter D and L before the name of any compound indicates the relative configuration of any particular stereoisomers of the compound with respect to configuration of some other compounds, the configuration of which is known. In case of carbohydrate, this refer to their relation with particular isomers. Glyceraldehyde. Glyceraldehyde contains one asymmetrical carbon atom and exists in two enantiomeric forms as shown below. So this is plus glyceraldehyde, this is minus glyceraldehyde, because in this OH group present in right side, so this is dextrorotatory, and in this minus glyceraldehyde OH present as left side, so this is levorotatory. Plus isomers of glyceraldehyde D configuration. It means that when structure of formula written on paper specific convention you will study in higher classes, the OH group lies on right hand side of structure. All those compounds which can be chemically correlated to D plus isomer glyceraldehyde are said to have D configuration, whereas those can correlate with to L isomer of glyceraldehyde are said to be L configuration. In L isomer, the OH group is on left side, as you can see the structure. For assigning the configuration of monosaccharides, it is lowest asymmetrical carbon atom as shown below, which is compared as in plus glucose. OH on the lowest asymmetrical carbon is on the right side, which is comparable to plus glyceraldehyde. So plus glucose is assigned D configuration. Other asymmetrical carbon atom of glucose are not considered for the comparison. Also, the structure of glucose and glyceraldehyde is written in a way most oxidized carbon in this case CHO at top, D glyceraldehyde. So D plus glyceraldehyde OH in right side direction, and D plus glucose. Here we can see the last carbon that the last OH that is attached to CH2OH is on right side. Cyclic structure of glucose. The structure first of glucose explain most of the property, but the following reaction of the fact cannot be explained by the following structure. First, despite having the aldehyde group, glucose does not give chief taste, and it does not form hydrogen sulfide addition product with NaHSO3. Second, the pentasterase of glucose does not react with hydroxylamine, indicating the absence of free CHO group. Third, glucose is found to exist in two different crystalline forms which are named as alpha and beta. The alpha form of glucose melting point 490 Kelvin is obtained by crystallization from concentrated solution of glucose at 303 Kelvin, while the beta form melting point 423 Kelvin is obtained by crystallization from hot and saturated aqueous solution at 371 Kelvin. The behavior could not be explained by the open chain structure first of glucose. It was proposed that one of the OH group may add to CHO group and form cyclic hemiacetal structure. It was found that glucose forms six-membered ring in which OH at C5 is involved in ring formation. They explain the absence of CHO group, also existence of glucose in two forms as shown below. These two cyclic forms exist in equilibrium with one chain structure. This is alpha D glucose and this is beta D glucose. The two cyclic hemiacetal form of glucose differ only in the configuration of hydroxyl group at C1 called anomeric carbon. So this is anomeric carbon. The aldehyde carbon before cyclization, such isomer that is alpha form and beta form are called anomers. The six-membered cyclic structure of glucose is called pyranose structure alpha or beta, is analogy with pyrene. Pyrene is cyclic organic compound with one oxygen atom and five carbon atom in the ring. The cyclic structure of glucose is more correctly represented as a Haworth structure as follows. So this is pyrene structure, pyrene, and this is alpha D glucopyranose, and this is beta D glucopyranose. So in alpha glucopyranose, this OH as first carbon is below, and at beta D glucose, this OH group is above. This is basic difference in alpha and beta cyclic structure of pyranose. 14.1.2.2 fructose. Fructose is important ketohexose. It is obtained along with glucose by hydrolysis of disaccharide sucrose. It is a natural monosaccharide found in fruit, honey, and vegetable. It is pure form. It is used as sweetener. It is also important ketohexose. Structure of fructose. Fructose also have a molecular formula 6H12O6, and on the basis of a reaction it was found to contain a cationic functional group at carbon number 2 and 6 carbon in straight chain as in case of glucose. It belongs to this series and is a lever rotating compound, is appropriate written as D minus fructose. It open chain structure as shown as below. So this is structure of fructose, open chain structure. Here is ketonic group. It also exists in two cyclic form which obtained by addition of OH at C5 to the C-double OH group. O group. The ring thus formed is 5-membered ring and is named as furanose. With analogy to the compound furan, furan is 5-membered cyclic compound with 1 oxygen and 4 carbon atoms. So this is furan. This is alpha D fructofuranose. This is beta D fructofuranose. In alpha D fructofuranose, OH is inside, and in beta D fructofuranose, OH is outside the cyclic ring. The cyclic structure of two anomers of fructose are represented by Haworth structure. This is alpha D fructofuranose. This is beta D fructofuranose. So in this Haworth structure, the first CH2 OH first carbon or OH is in lower side, and in beta defructofuranose OH is at upper side. This is basic or only difference between alpha and beta fructofuranose. So in alpha this is lower, in beta this is upper. Alpha OH is lower, beta is upper. All BU. 14.1.3 disaccharides. You have already read that disaccharides on hydrolysis will dilute acid or enzyme yield two molecules, either the same or different monosaccharides. The two monosaccharides are joined together by an oxide linkage formed by loss of water molecules. Such a linkage between two monosaccharide units through oxygen atom is called glycosidic linkage. In disaccharides, if the reducing group of monosaccharide, that is aldehyde, and ketonic group are bonded, these are non-reducing sugars, that is sucrose. On the other hand, sugars in which these functional groups are free are called reducing sugars. For example, maltose and lactose. Sucrose, one of the common disaccharides, sucrose, which on hydrolysis give equimolar of D plus glucose and D minus fructose. This is sucrose plus water form D glucose and D fructose, D minus fructose. This is dextrorotatory and this is levorotatory. These two monosaccharides are held together by glycosidic linkage between C1 of alpha D glucose and C2 of beta D fructose. Since the reducing group of glucose and fructose involved in the glycosidic bond formation, sucrose is non-reducing. So this is alpha D glucose and this is beta D fructose, and this is structure of sucrose formed by alpha D glucose and alpha D fructose, beta D fructose, and these are joined by glycosidic linkage. Sucrose is dextrorotatory, but after hydrolysis give dextrorotatory glucose and levorotatory fructose. So this is what? This is levorotatory fructose and this is dextrorotatory glucose. Since the lever rotation of fructose is minus 92.4 is more than dextrorotation of glucose plus 52.5 degree, the mixture is levorotatory. Thus, hydrolysis of sucrose bring about change in the sign of rotation from dextro plus to levo minus, and production is named inward sugar. Second, maltose. Maltose, another disaccharide. Maltose is composed of two alpha D glucose units in which C1 of glucose first is linked to C4 of another glucose unit second. The free aldehyde group can be produced at C1 of second glucose in solution and its so reducing properties, so it is reducing sugar. This is maltose made of alpha D glucose and alpha D glucose, 2 alpha D glucose, and joined by glycosidic linkage for maltose. Maltose made of 2 alpha D glucose. Third, lactose. It is more commonly known as milk sugar since this disaccharide is found in milk. It is composed of beta D galactose and beta D glucose. The linkage between C1 of galactose and C4 of glucose free aldehyde group may be produced at C1 of glucose units, hence it is also reducing sugar. This is lactose made up of beta D galactose and beta D glucose. 40.1.4 polysaccharides. Polysaccharides contain a large number of monosaccharides units joined together by glycosidic linkage. These are most commonly encountered carbohydrates in nature. They mainly act as food storage of structure. First, starch. Starch is mainly storage polysaccharides of plant. It is most important dietary source for human beings. High content of starch is found in cereals, root tubers, and some vegetables. It is a polymer of alpha D glucose, consists of two components, amylose and amylopectin. Amylose is a water-soluble component which constitutes 15 to 20% of starch. Chemically, amylose is a long unbranched chain with 200 to 1000 alpha D glucose units held together with C1 and C4 glycosidic linkage. Amylopectin is soluble in water and constitutes 80% to 85% of starch. It is branched and chain polymer of alpha D glucose units in which chain is formed by C1 and C4 glycosidic linkage, whereas branching occurs C1 and C4 glycosidic linkage. This is amylose. This is alpha link C1 at C1 and C4 carbon. This is alpha link. This is structure of amylose. This is structure of amylopectin. So branching occur at C1 and C6 carbon, and these are same as amylose. The difference between amylose and amylopectin is of only this branching. If we cut this branch, we can say uh, amylose. We can say amylose and amylopectin are similar. Second, cellulose. Cellulose occur exclusively in plants and it most abundant organic substance of plant kingdom. It is predominant constituent of cell wall of plant cell. Cellulose is straight chain polysaccharide composed of only beta D glucose units which are joined together by glycosidic linkages C1 and C4 of next glucose molecule. So this is structure of cellulose made up of only straight chain and joined at C1 and C4 carbon. This is C1 and this is C4 carbon of beta D glucose. So this is beta D glucose. Third, glycogen. The carbohydrates are stored in animal body as glycogen. It is also known as animal starch because its structure is similar to amylopectin and is rather more highly branched. It is present in liver, muscles and brain. When the body needs glucose, enzyme break the glycogen down to glucose. Glycogen is also found in yeast and fungi. 14.1.5 Importance of carbohydrates. Carbohydrates are essential for life in both plants and animals. They form major portion of our foods. Honey has been used for a long time as an instant source of energy by whales in Ayurvedic system of medicine. Carbohydrates are used as storage molecule as starch in plant and glycogen in animals. Cell wall of bacteria and plants is made up of cellulose. We build furniture etc. from cellulose in the form of wood and clothe ourselves with cellulose in the form of cotton fibers. They provide raw materials many important industries like textiles, paper, lacquers, breweries, etc. to aldopentose, namely D-ribose and 2-deoxy-D-ribose. Section 14.5 class 12. The presence of nucleic acid. Carbohydrates are found in biosystem in combination with many proteins and lipids. 14.2 Proteins. Proteins are the most abundant biomolecules of living system. Chief sources of proteins are milk, cheese, pulse, peanuts, fish, meat, etc. They occur in every part of plant to form the fundamental basis of structure and function of life. They are also required to growth and maintenance of body. The word protein is derived from Greek word proteose, which means primary or primary importance. All proteins are polymer of alpha amino acids. 14.2.1 Amino acids. Amino acids contain amino, NH2 and carboxyl C11OH functional group. Depending upon the relative position of amino group with respect to carboxylic acid, the amino acid can be classified as alpha, beta, gamma and delta and so on. Only alpha amino acids are obtained on hydrolysis of proteins. They may be contain other functional group also. These are alpha amino acids. All alpha amino acids have tribal name which usually reflect property of compounds or its source. Glycine is named since it has sweet taste, that is glycose means sweet. The tyrosine was first obtained from cheese. In Greek, tyros means cheese. Amino acids are generally represented by 3 letter symbols. Sometimes 1 letter symbol is also used. Structure of some commonly occur amino acid along with their 3 letter and 1 letter symbols are given in table 14.2. So 14.2 Nature of amino acids. Name of amino acid. Characteristic feature of side chain are 3 letter symbols and 1 letter codes. So this is glycine, and in place of alkyl group hydrogen present, and this is represented by gly and G, Gauli, and alanine in in presence of R CH3 present, and in valine are replaced by CH 2 methyl alkyl 2 methyl ethyl group, and in leucine are replaced by this, and in isoleucine arginine lysine glutamic acid aspartic acid glutamic acid aspargine threonine serine cysteine methionine phenyl alanine tyrosine tryptophan histidine proline and so on. So tryptophan, histidine and proline, these are cyclic amino acid, cyclic structure present in this amino acid, and glutamic acid, aspartic acid, these are HD and many more, and this is simplest. Glycine is simplest amino acid. 12.2.2 Classification of amino acids. Amino acids are classified as acid, basic and neutral depending upon the relative number of amino and carboxyl group in their molecules. Equal number of amino and carboxylic group makes it neutral. More number of amino than carboxylic group make it basic, and more carboxylic group as compared to amino group make it acidic. The amino acids which can be synthesized in body are known as non-essential amino acids. On the other hand, those which cannot be synthesized in our body must be obtained through diet is known as essential amino acid. So essential amino acids marked by *6 in these tables. Amino acids are usually colorless crystalline solids. These are water soluble, high melting solids and behave like salts rather than simple amines or carboxylic acids. This behavior is due to the presence of both HD carboxyl group and basic amino group in the same molecules. In aqueous solution, the carboxyl group can lose a proton and amino group can accept proton, giving rise to dipolar ion known as deuterion. This neutral but contain both positive and negative charges. This is deuterionic form of amino acids. Deuterionic form of amino acids show amphoteric behavior and react with both acid and base. So this is for so amphoteric due to presence of basic and HD group. Except glycine, all other naturally occurring alpha amino acids are optically active, because in glycine there are two hydrogen present at same carbon. So this carbon is not chiral, hence this is asymmetrical. These exist both in D and L form. Most natural occurring amino acids have EL configuration. EL amino acids are represented by writing NH2 group on left hand sides. 12.2.3 Structure of protein. You have already read that the proteins are polymers of alpha amino acids and they are connected to each other by peptide or peptide linkage. Chemically, peptide linkage is an amide formed between C1OH group and NH2 group. The reaction between two molecules of similar or different amino acids proceeds through the combination of amino group of one molecule with hydroxyl group of other. This result in the elimination of water molecule and formation of peptide bond CONH. The product of reaction is called dipeptide because it made up of two amino acids. For example, when carboxylic group of glycine combine with amino acid of alanine, we get dipeptide glycine alanine. So this is glycine alanine formed by dipeptide linkage. If third amino acid combined with dipeptide, each product is called tripeptide or tripeptide amino acid. Three amino acid linked by two peptide linkage. Similarly, when 4, 5, 6 amino acid linked, the respective product is known as tetrapeptide, pentapeptide or hexapeptide respectively. When the number of such amino acid is more than 10, then the product are called polypeptides. A polypeptide with more than 100 amino acid residue having molecular mass higher than 10,000 unit is called a protein. However, the distinction between the polypeptide and protein is not very sharp. Polypeptides is fewer amino acids are likely to be called protein if they orderly have well defined conformation of proteins such as insulin, which contain 51 amino acids. Protein can be classified into following two types on the basis of their molecular shape. First, fibrous protein, and second is globular protein. When the polypeptide chain run parallel and held together by hydrogen and disulfide bond, then fiber-like structure is formed. Such proteins are generally insoluble in water. Some common examples are keratin present in hair, wool, silk, and myosin present in muscle, etc. This structure results when the chain polypeptide coil around their spherical shape. These are usually soluble in water. Insulin and albumin are common examples of globular proteins. Structure and shape of protein can be studied at four different levels, that is primary, secondary, tertiary, and quaternary, each level being more complex than the previous one. First, primary structure of protein. Protein may have one or more polypeptide chain. Each polypeptide in a protein has amino acid linked with each other in a specific sequence, and its sequence of amino acid that is said to be primary structure of protein. Any change in primary structure of that is primary structure, the change in amino acid create different protein. This is alpha helix structure of protein. Second is secondary structure of protein. This secondary structure of protein refers to the shape in which long polypeptide chain can exist. They are found to exist in two different types of structure, namely alpha helix and beta pleated sheet structure. These structures arise due to regular folding in backbone of polypeptide chain due to hydrogen bonding between C double bond O and NH group of peptide bond. Alpha helix is one of the most common way in which a polypeptide chain form all possible hydrogen bond by twisting into right-handed screw helix with the NH group of each amino acid residue hydrogen bonded to the SCO of adjacent turn of helix shown in figure 14.1. Beta pleated sheet of structure of protein. In beta pleated sheet structure of all protein, chain are stretched out to nearly maximum extension and then laid side by side, which are held together by intermolecular hydrogen bonds. The structure resembles the pleated folds of drapery and therefore known as beta pleated sheet. Third, tertiary structure of protein. The tertiary structure of protein represents overall folding of the polypeptide chain, that is for the folding of secondary structure. It gives to two measures molecular shape, namely fibrous and globular. The main forces which stabilize tertiary structure of protein are hydrogen bonds, disulfide linkage, van der Waals, and electrostatic force of attraction. For quaternary structure of protein, some of the proteins are composed of two or more polypeptides and referred to as subunits. The spatial arrangement of subunits with respect to each other are known as quaternary structure. A diagrammatic representation of all these four structures is given figure 14.3, where each colored bar represented amino acids. Figure 14.3 diagrammatic representation of protein structure, two subunits, and two type of quaternary structures. This is primary, this is secondary structure, and this is tertiary structure, and this is quaternary structure. 40.4 primary, secondary, tertiary, and quaternary structure of hemoglobin. So A primary structure, and this is secondary structure. This is tertiary structure. This is quaternary structure of hemoglobin. 40.2.4 denaturation of proteins. Proteins found in biological system is unique three-dimensional structure of biological activity called native proteins. When a protein is native form is subject to physical change like change in temperature or chemical change like change in pH, the hydrogen bond is distributed. Due to this, globular fold and helix get uncoiled and protein loses the biological activity. This is called denaturation of protein. During denaturation, secondary tertiary structure are destroyed but primary structure remain intact. The coagulation of egg white on boiling in common example of denaturation. Another example of curdling of milk which is caused by due to formation of lactic acid and bacteria present in the milk. 40.4 40.3 enzymes. Life is possible due to coordination of various chemical reactions in the living organism. An example of digestion of food, absorption of appropriate molecule of, and ultimately production of energy. This process involves sequence of reaction and all these reactions occur in the body under very mild conditions. This occur with the help of certain biocatalysts called enzymes. Almost all the enzymes are globular proteins. Enzymes are very specific for a particular reaction and for a particular substrate. They generally named after compounds or class of compounds upon which they form. They were, for example, the enzyme catalyzed hydrolysis of maltose with glucose and named as maltase. Maltase formed 2 glucose on hydrolysis. A maltase enzyme. Sometimes enzymes are also named after reaction where they are used. For example, the enzyme which catalyzes the oxidation of substrate with simultaneously reduction and another substrate are named oxidoreductase enzyme. The ending of name of an enzyme is HH. 14.3.1 Mechanism of enzyme reaction. Enzymes are needed in a very small quantity for progress of reaction, similar to the action of chemical catalyst. Enzymes are said to reduce the magnitude of activation energy. For example, activation energy of acid hydrolyzed sucrose is 6.22 kJ per mole, while the activation energy is 2.15 kJ per mole when hydrolyzed by enzyme sucrase. Mechanism for enzyme action has been discussed in Unit 5. 12.4 Vitamins. It has been observed that certain organic compounds are required in a small amount in our diet, but their deficiency causes a specific disease. This compound is called vitamins. Most of the vitamins cannot be synthesized in our body, but plants can synthesize almost all of them, so they are considered as essential food factors. However, the bacteria of guts can produce some of the vitamins required by us. All the vitamins are generally available in our diet. Different vitamins belong to various chemical classes. It is difficult to define them on the basis of structure. They are generally regarded as organic compound required in diet a small amount of perform a specific biological function for normal maintenance of for optimal growth and health of organism. Vitamins are designated by alphabet A, B, C, D. Some of them further named as subgroup, that is B1, B2, B6 and B12 etc. Excess of vitamin C is also harmful and vitamin pills should not be taken without the advice of doctors. The term vitamin was coined from word vital plus amine, since the earlier identified compound had amino groups. Later work showed that most of did not contain amino groups, so the letter E was dropped and term vitamin is used these days. 40.1 4.1 Classification of vitamins. Vitamins are classified into two groups depending upon the solubility in water or fat. First, fat soluble vitamins. Vitamins which are soluble in fat or oil but insoluble in water is kept in this group. These are vitamins A, D, E and K. They are stored in liver adipose fatty tissue. Second, so fat soluble vitamin are A, D, E and K. Water soluble vitamins. B group vitamins and vitamin C are soluble in water, so they are grouped together. Water soluble vitamins must be supplied regularly in our diet because they are rarely excreted in urine and cannot be stored except B12 in our body. Some important vitamins and their sources are disease caused by deficiency listed in table 14.3. Table 14.3, some important vitamins and their sources, their deficiency diseases. So these are vitamins names here, and these are sources and the deficiency diseases. First, vitamin A, obtained from fish liver oil, carrots, butter, and milk. And the deficiency of vitamin A causes xerophthalmia, hardening of cornea, and night blindness. And second is vitamin B1, thiamine. It is obtained from yeast, milk, green vegetables, and cereals. De- Deficiency diseases are very loss of appetite and retarded growth. Third, vitamin B2, riboflavin, obtained from milk, egg white, liver, and kidney. And deficiency diseases, chillosis, fizzying at the corner of mouth and lips, digestive disorders, and burning sensation of skin. And four is vitamin B6, also known as pyridoxine, obtained from yeast, milk, egg yolk, cereals, and grams. Its deficiency causes convulsions. And B12, obtained from meat, fish, egg, and curd. And deficiency diseases, pernicious anemia, RBC deficiency in hemoglobin. Vitamin C, also known as ascorbic acid, obtained from citrus fruit, amla, green leafy vegetables. Its deficiency causes scurvy or bleeding gums. Vitamin D, exposure we can get from sunlight and fish and yolk, and its deficiency causes rickets, bone deformities in children, osteoporosis, osteomalacia, soft bone, and joint pain in adults. Vitamin E, obtained from vegetable like wheat, germ oil, sunflower oil, etc. Its deficiency increases fragility of RBC and muscular weakness. Vitamin K, obtained from green leafy vegetables, and deficiency causes increase in blood clotting time. 14.5, nucleic acid. Every generation of each and every species resembles its ancestor in many ways. How are these characteristics transmitted from one generation to next? It has been observed that nucleus of living cell is responsible for transmission of inherent characters, also called heredity. The particles in nucleus of the cell responsible for the heredity are called chromosomes, which are made up of protein and another type of biomolecules called nucleic acid. These are mainly of two types: deoxyribonucleic acid (DNA) and ribonucleic acid (RNA). Since nucleic acid are long polymer nucleotides, so they are called polynucleotides. James David Watson. So, born in Chicago, Illinois in 1928, Watson received his PhD in 1950 from Indiana University in zoology. He is best known for his discovery of structure of DNA, which he shared with Francis Crick and Maurice Wilkins in 1962 Nobel Prizes Physiology and Medicine. They proposed that DNA molecules take place the shape of double helix, an elegantly simple structure that resembles a gently twisted ladder. The rails of the ladder are made up of alternative units of phosphate and sugar deoxyribose. The lungs and each composed of pair of purine pyrimidine bases. This research led to foundation of emerging field of molecular biology. The complementary pairing of nucleotide base explain how identical copies of parental DNA passes on to two daughter cells. This research launched a revolution in biology, led to modern recombinant DNA technology. 40.5.1, chemical composition of nucleic acid. Complete hydrolysis of DNA and RNA yields pentose sugar, phosphoric acid, on and nitrogen containing heterocyclic compounds called bases in DNA molecules. This sugar moiety beta D2-deoxyribose, whereas in RNA molecules it is beta D ribose. So this is beta D ribose. We can see OH group is above, and this is beta D2-deoxyribose. So after removal of OH group, it become beta D 2 deoxyribose. This OH group is removed from second carbon. DNA contains 4 bases, namely adenine, guanine, cytosine, thymine. RNA also contains 4 bases. The first 3 bases are same, but fourth base in RNA, uracil, is in place of thymine. This is adenine, this is guanine, this is cytosine, and this is thymine, and this is uracil. These are purines, and these are pyrimidines. 14.5.2 Structure of nucleic acids. A unit formed by new attachment of a base to one dash position of sugar is called nucleoside. In nucleoside, the sugar carbon is numbered as 1 dash, 2 dash, 3 dash, etc. In order to distinguish this from the base 14.5, when nucleoside is linked to phosphoric acid at 5 prime position of sugar moiety, we get nucleotide 14.5. 14.5 is structure of A nucleoside and B is nucleotide. So this is structure of nucleoside. In this base and base attached to sugar. This is nucleoside contain base plus sugar, but nucleoside also contain phosphate group. So nucleotide contain base plus sugar plus phosphate group. Nucleotides are joined together by phosphodiester linkage between 5 prime and 3 prime carbon atom of pentose sugar. The formation of typical dinucleotide is shown in figure 40.6. So formation of dinucleotides. So these are two nucleotides, and these are joined together by phosphodiester linkage at 3 prime and 5 prime location, and these form dinucleotides, means two nucleotides joined together. In simplified version of nucleic acid chain as shown below. So these are simplified structure denotation of this diagram. So base, sugar, phosphate, this form one nucleotide, and base, sugar, phosphate, this form another nucleotide, and these are bonded by phosphodiester linkage and so on to form a nucleotide. To form DNA. This is double strand helix of DNA given by Francis and Crick. Information regarding the sequence of nucleotide in chain of nucleic acid is called primary structure. Nucleic acid have secondary structure also. James Watson and Francis Crick have double strand helix structure of DNA. Two nucleic acid chain are wound about each other and held together by hydrogen bond between pairs of bases. The two strands are complementary to each other because the hydrogen bonds are formed between specific pairs of bases. Adenine forms hydrogen bond with thymine, whereas cytosine forms hydrogen bond with guanine. The secondary structure of RNA single strand helices is present, which sometimes folds back on itself. RNA molecules are of three types and they perform different functions. They are named as messenger RNA, mRNA, RNA, ribosomal RNA, and tRNA, transfer RNA. Har Gobind Khorana. Har Gobind Khorana was born in 1922. He obtained MSc degree from Punjab University in Lahore. He worked with Professor Vladimir Prilog, who molded Quran thought and philosophy toward science, work and effort. After a brief stay in India in 1949, Khorana went back to England and worked with Professor D. Jablochiner and Professor A.R. Todd. It was at Cambridge, UK, that he got interested in both proteins and nucleic acids. Dr. Khorana shared the Nobel Prize of Medicine and Physiology in 1968 with Marshall Nirenberg, Robert Hawley for cracking genetic code. DNA fingerprinting. It is known that every individual has unique fingerprints. These occur in the tips of finger and have been used for identification for a long time, but this can be altered by surgery. A sequence of DNA on a sequence of base on DNA also unique for a person, and information regarding this called DNA fingerprinting. It is same for every cells and cannot be altered by any known treatment. DNA fingerprinting is now used as first in forensic laboratories for identification of criminals, second to determine paternity of an individual, third to identify the dead bodies in any accidents by comparing DNA parents or children, four to identify racial group to rewrite biological evolution. 40.5.3 Biological function of nucleic acids. DNA is chemical basis of heredity and may be regarded as reserve of genetic information. DNA is exclusively responsible for maintaining the identity of different species of organisms over millions of years. All DNA molecule is capable of self-replication during cell division, and identical DNA strands and transfer to daughter cell. Another important function of nucleic acid is to transfer protein synthesis in proteins in the cell. Actually, the protein is synthesized by various RNA molecules in the cell, but the message for synthesis of particular protein is present in DNA. 40.6 Hormones. Hormones are molecules that act as intercellular messenger. These are produced by endocrine gland in body and poured directly into the blood stream, with transport them to site of action. The term chemical nature of some of these steroids, that is estrogen and androgen, some are polypeptides, for example insulin and endomorphins, and some other are amino acid derivatives such as epinephrine and non-epinephrine. Hormones have several functions in body. They help to maintain the balance of biological activity in body. The role of insulin keeping the body blood glucose level within the narrow limit, for example, is an example of this function. Insulin is released in response to rapid rise in blood glucose level. On the other hand, hormone glucagon tends to increase the blood glucose level in the body. The two hormones together regulate the glucose level in the body. Epinephrine and norepinephrine mediate the response to external stimuli. Growth hormone and sex hormones play a role in growth and development. Thyroxine produced in thyroid gland is an iodinated derivative of amino acid tyrosine. Abnormally low level of thyroxine led to hypothyroidism, which is characterized by letharginess and obesity. Increased level of thyroxine causes hyperthyroidism. Low level of iodine in diet may lead to hypothyroidism and enlargement of thyroid glands. This condition is largely being controlled by adding sodium iodide to commercial salts, iodized salt. Steroid hormones are produced by adrenal cortex and gonad testes in male and ovaries females. Hormones released by adrenal cortex play a very important role in function of body. For example, glucocorticoids control carbohydrate metabolism, modulate inflammatory reaction, and are involved in reaction of auto stress. The mineralocorticoids control the level of excretion of water and salt by kidney. The adrenal cortex does not function properly, and one of the results may be Addison disease characterized by hypoglycemia, weakness, and increased susceptibility to stress. The disease is fatal unless it is treated by glucocorticoids and mineralocorticoids. Hormones released by gonads are responsible for development of secondary sex characters. Testosterone is the major sex hormone produced in males. It is responsible for development of secondary male characteristics, deep voice, facial hair, general physical constitution, and estradiol in the man-female sex hormone. It is responsible for development of secondary female characteristics and participates in the control of menstrual cycle. Progesterone is responsible for preparing uterus for implantation and of fertilized egg. So here we go for summary. Carbohydrates are optically active polyhydroxyaldehyde or ketone of molecule which provide such unit on hydrolysis. They are broadly classified into three groups. For example, monosaccharide, disaccharide, and polysaccharides. Glucose, the most important source of energy for mammals, is obtained by digestion of starch. Monosaccharide held together by glycosidic linkage to form disaccharide or polysaccharides. Proteins are polymers about 20 different alpha amino acids which are linked by peptide bonds. 10 amino acids are essential amino acids because they cannot synthesize by our body, hence must be provided out through diet. Proteins perform various structure and dynamic function in the organism. Protein which contain only alpha amino acids are called simple proteins. The secondary and tertiary structure of protein get reduced on change of pH, temperature, and they are not able to perform the functions. This is called denaturation of proteins. Enzymes are biocatalysts which speed up the reaction in biosystems. They are very specific and selective in their action, and chemically enzymes are all proteins. Vitamins are essential food factors required for the required diet. In the classified, this is classified as fat soluble like A, D, E, and K, and water soluble like B and C. Deficiency vitamins lead to these diseases. Nucleic acids are polymers of nucleotides which in turn consist of base of pentose sugar and phosphate moiety. Nucleic acids are responsible for transfer of characters from parent to offspring. There are two types nucleic acid, DNA and RNA. DNA contains a 5-carbon sugar molecule called 2-deoxyribose, whereas RNA contains ribose. Both DNA and RNA contain adenine and guanine and cytosine. The fourth base is thymine in DNA and uracil in RNA. The structure of DNA and double strand, whereas RNA is single strand molecule. DNA is the chemical basis of heredity and have cold message of protein synthesis in cell. There are 3 types of RNA: mRNA, rRNA, tRNA, which annually carry out protein synthesis. So मेरे भाई, कीटोन, एल्डिहाइड, कार्बोक्सिलिक एसिड्स, अमाइंस, बायोमोलिक्यूल्स, ये सिंगल वीडियो में अपना कंप्लीट हो गया. सिर्फ रीडिंग था, नो एक्सप्लेनेशन. और पहले भी हम लोग कर चुके हैं एल्कोहल, फेनॉल, ईथर्स, हेलो एल्केन एंड हेलोएरिन्स. ये पहले भी इनका सेपरेट वीडियो में कर चुके हैं और इस वीडियो में पूरे तीनों चैप्टर्स कवर कर लिए. तो एनसीईआरटी रीडिंग सेकेंड का कंप्लीट हो गया, क्लास 12 का पार्ट सेकेंड का. और ऐसे ही पढ़ते रहो, रीडिंग लगाते रहो भाई. मेन है एनसीईआरटी से ही क्वेश्चन आने हैं. कंसेप्ट जो नहीं आ रहा उसको सीखो, उसको सीखना पड़ेगा. जैसे SN1 2 SN1 वो सब तो सीखना पड़ेगा मैकेनिज्म, बट एनसीईआरटी का रिएक्शन वगैरह तो रट्टा करना पड़ेगा ना. चलते हैं भाई, गुड बाय.